Good morning, everyone, and welcome to the second day of the Program Review Days 2020. My name is Antonio Aguiló. I am a project officer at the Fuel Cells and Hydrogen Joint Undertaking, and I will be moderating this session. For this morning, we have two parallel sessions in which you will hear from a number of projects in the area of stationary applications of fuel cells. The session you are in right now will present a number of projects that are demonstrating and deploying systems in real installations. Immediately after these parallel sessions, we will have an additional one with presentations from our research projects in this area. As you will see in the next three presentations that will follow, fuel cells are already providing clean heat and power for a number of end-use applications. Fuel cells are efficient electrochemical devices. They do not rely on combustion. They are efficient electrochemical devices, and they are already reducing CO2 emissions and improving the air quality relative to conventional technologies. And I have to say this is a sector that is also contributing already to improve air quality, as I mentioned, but to also increase new skills and new jobs in Europe across the whole value chain. Not only in the research community, but also jobs in the manufacturing sector and also blue-collar workers for servicing and maintaining these systems. And you will see how the next presentations will provide real examples of all of this. First one on residential sector and small businesses applications. Second one on portable generation using hydrogen gensets. And the last one looking at applications in the commercial and service sector. I want to encourage you to please use the question button that is available in your screen or through the Mentimeter application. At the end of the three presentations, we will have around 25-30 minutes to answer them. So you are encouraged to send out your questions to make the discussions as dynamic and interesting as possible. And you are also invited to post any questions in relation to the presentations that were done yesterday on the portfolio of our activities on stationary fuel cells. So, without further delay, I'm very glad to give the floor to Mr. Andreas Frommel from Sunfire, that today will present the activities of the PACE project on behalf of the project consortium, looking at demonstration of fuel cell systems for the residential and small service sector. Andreas, the floor is yours. Thank you.
Yeah, many thanks, Antonio, for this kind introduction. And hopefully you can see now the slides. I'm starting with a quick overview about the CHP, the micro CHP. I expect that we now see the movie.
You like to keep the lights on when enjoying dinner with friends and family. At the end of a long working day, you unwind by cuddling up on the sofa with your tablet, reading an ebook, or watching your favorite TV show. Now you can do all this while protecting the environment and keeping your energy bills down. Fuel cell micro-cogeneration is a state-of-the-art home energy system that brings sustainable, reliable, and affordable energy to your home. With fuel cell micro-cogeneration, you can generate your own electricity while producing heating, hot water, and even cooling at the same time. In his house, Peter installed a unit which reduces his energy bill by €700 every year, saves him 2 tons of CO2 annually, and helps him to produce his own electricity for his home appliances and electric car, as well as to put the extra electricity on the grid. The EU co-funded project PACE aims to deploy more than 2,800 fuel cell units across 10 European countries in households and small businesses by 2021. Fuel cell units installed under the PACE project empower citizens to become active participants in Europe's energy transition. Surveys show that more than 90% of fuel cell owners are pleased with the environmental performance, the comfort and warmth, reliability and running costs of their unit. Fuel cells micro-cogeneration is here, it works, and you can benefit from it today.
So, everything is said, I can say, about the micro CHP. You see the companies involved in this PACE project, and I'm happy to represent them today. The companies providing micro CHP fuel cells for this really large demonstration project. What could a residential CHP provide to the energy transition? You see that we here could provide power and heat, the combined power and heat CHP, which has a benefit that we have the highest possible efficiency using different fuels, LPG, natural gas, biogas, and provide power even during the winter time, during time with no wind, then during the night, providing the power to electrical cars as well as to heat pumps. And it's a great complementary technology to PV, because once the lower profile is in the winter time, the fuel cell could step in and provide the power to the residential building. The aim of the PACE project is to shorten the gap between pure R&D funding and the pure commercial market. So a large demonstration project to develop at the same time the European manufacturing structure, supply chain for the fuel cells, as well as developing a next generation with cost down, with higher efficiency, with a better connection to the internet, with apps and so on, to move forward with the whole sector. And that's I would say a great demonstration how public-private money being combined could deploy the whole sector in the fuel cell area, as well as we see later these days with the hydrogen sector. And the outcome is that we now could see moving really good forward. We deployed the units. As you see, it's a huge project. We may have a longer duration of the project during to the COVID crisis, but we are on a good track. You'll see that in a minute, to deploy the market and install all these different units. This means we are in the next generation. So we provide generation 2, as we name that, with lower cost, higher efficiency, during the different technologies. And the different technologies you can see here are coming from different OEMs, technologies in the direction of PEM as well as SOFC. SOFC mostly from European sources, PEM from Japanese sources, and then integrated in a heating equipment of leading heating equipment provider in Europe in 2 different ways. One is to have a separated tool, a box you can say, combined with a peak burner. And the second is to have this unit, the fuel cell, integrated in a unit with the peak burner and sometimes also with the heating storage, the hot water storage. So those are the different strategies and also the different application able to be integrated in several different infrastructures in the single-family houses, because that's the aim, to replace existing heating boilers, for instance, based on heat oil. We have to replace them because we now could reach a tremendous CO2 reduction by using the fuel cells. We made progress. You see that the starting point here, and then step by step, the fuel cells were installed. We are on a good way to reach the 2,800 units by end of next year in time, and really spread on the target countries we had in focus for this huge reference or demonstration project. What are the customers? So we mostly have the owner of the house as a customer, and in most cases, as you see on the left-hand side, these are buildings with 2 to 4 people living there, so family houses. But we have also a movement in the direction that we have a share of small business houses. And here you see the benefits the customers are heading for, the benefits in direction of being more independent from cost development in the energy market, sustainable solution, clean energy with no pollution, with no burning of the fuels, as well as CO2 reduction, and of course also cost reduction. And you know that probably from the outcome of Enerfield, that customers have mostly 600 to 800 euro per month cost savings coming from the fuel cell. So we see also savings in the direction of over 1,000 euro, 1,300 euro, something like that. But the most motivation of the customer is to have a sustainable solution, also able to be provided to their children in the future. Look, this is something we installed. And also, as you have seen in the movie, with the fuel cell, with the CHP fuel cell, you could combine the consumption and the production within the distribution grid, and not burden the flexibility or the disflexibility of the certain technologies towards the transmission grid. You could provide the power to the battery combined with the PV, and so you could flatten the residual profile being fed by that transmission grid. That's a huge benefit, I would say. And here you could also see the typical houses for our fuel cells. So it's a single-family house, but we see also a movement or development towards cascades of fuel cells or several small fuel cells within small business buildings or combined buildings, so flats and offices. And then also as you have seen previously, the units providing 1.5 kilowatt hours electrical power, they could step in and provide the power to for instance, a small pension or a little hotel or things like that. So the conclusion is, with micro CHP, that's the best method today to use fossil fuels, because we have the highest possible efficiency since we combine power production and heat production. But that's not a stranded asset. So as you know, the fuel cell is not burning the fuel, electrochemical conversion, which means at the end we have hydrogen in. And this opens the way for the future. But you could save CO2 today with this technology, and you could live with this technology in the future once we have the hydrogen infrastructure ready and the units can run on pure hydrogen. So that's I would say a great combination between right now a technology available and the future purpose of this. And then we have a great infrastructure, a great sector in Europe, having all these parts available for the fuel cell industry. And this opens the way towards, I would say, a powerful fuel cell sector for micro CHP in Europe. I want to show you at last, and last but not least, an interesting slide relative to our activities. So we did a lot. Sorry, it was too fast. We did a lot for dissemination, and you see some of these units in operation or on the fairs as well here. Of course, we are active. We have to do something on the way to the success. And the last slide I want to show you is this one here, to see, and we are proud about that, how many hours, more than 3 million operating hours we already had, and the power produced by all these fuel cells in pace. Thank you for your attention.
Thank you. Thank you very much, Andrea, for your presentation. I mean, it's great to see not only the overview of where we are or where European industry is with the deployment, but also to hear the voice of the customer, which eventually, of course, it's key to building market confidence. So thank you very much for that. And I'm now very happy to pass the floor to Mr. Stefano Barberi from RINA Consulting. Stefano is the project coordinator of the Everywhere project. And the project aims at developing, demonstrating hydrogen gensets across temporary events in Europe. Stefano, the floor is yours. Thank you.
Thank you very much, Antonio. I hope you can hear me well. My name is Stefano Barberis, and I'm glad here today to report you and present you the updates about our Everywhere project. As you said, the goal of Everywhere is to realize 8 fuel cell-based genset that should be used instead of traditional diesel genset, in temporary events, construction site, and music festival. This type of genset has to be first of its kind. Therefore, it is a very challenging project that involves technology providers coming from both the fuel cell sector as well as power converter experts, battery experts, and so on, because we had to put together the expertise of different partners as well as also the expertise of potential end users, like the presence of a music festival representative like D1 Green Music Initiative partner and Acciona as construction site and construction company interested to increase the sustainability of their site using our zero emission genset. The goal of Everywhere is indeed to use such gensets in urban application. The role of cities is indeed very crucial for us. And therefore, we have also the support from ICLEI European Secretariat in order to promote our gensets among cities in terms of policies and regulation. In this moment where we are more or less at half of the project. We have already achieved one of the first main objective, which is the setup of the design of our genset. It is a two-box approach. Indeed, our genset is composed by a bundle of pressurized hydrogen storage realized by Mytec and Linde, and a 10-feet container that integrates the power electronics and the fuel cell subsystem. In this moment, we have the pleasure, indeed, that after 2.5 years of challenging weeks and works, also unfortunately facing in the last 6 months the difficult COVID-19 situation, we are now glad to say that we have the first batch of our 8 genset ready, and I will show you them later on. So, let me say that we are at half of our project, and we, as I said, more or less achieved a part of the work. Indeed, in this moment, we are validating, as I said, the first batch of our genset, and the goal of the realization of our prototype is not only to realize prototypes that can work, but also realize prototypes that can be, let me say, interesting for the end user. At this purpose, we interacted a lot with potential stakeholders and potential end users, particularly rental companies, and we found that the short-term market, short-term rental market, like, for example, the rental of gensets for events, fairs, etc., could be the best option. In any case, it could be the best option because it is a market that currently is looking at prices of electricity around €1 per kilowatt hour in terms of LCOE. But in any case, it requires capex that cannot exceed, if possible, €2,000 per kilowatt. This is a tricky point for us because, of course, we have to rely not only on depreciation and decreasing of the cost of our fuel cell subsystem and hydrogen components, but at the same time we have also to rely on the reduction of costs like power converters, battery, etc. So it is a very challenging point, but we are glad to showcase you today the first pictures of our genset. As you can see, we are talking about two bundles, two boxes as we call. One is the power converter, the power genset that is composed by mostly a 10 feet container with a distribution socket panel on the rear of the container. That is something like very, very similar to traditional diesel genset. This container is composed by three rooms. One that is the electricity room where we have the control system and the power converter. The middle room where we have the thermal management and cooler of the fuel cell subsystem. And the front room where we have the fuel cell subsystem itself, where via an hydrogen conditioning and management panel, you are able to connect via a hydrogen pipeline to the bundle which is the pressurized hydrogen storage that, as I said, has been realized by Linde and Mytec, while the fuel cell genset, so the container, has been the result of orchestra work of 6 partners: THT, who took care of the mechanical integration, 3M, who took care of the electric integration, Gemport, who supervised the development of the control and, generally speaking, supervised the realization of the genset, Linde for sure for hydrogen management, VDT for our support, and PowerCell Sweden for the provision of the fuel cell subsystem, of course. As I said, this is the use of our genset is not only challenging for cost and realization, but also for aspects related to the demonstration, like, for example, regulatory aspects. Indeed, the permitting and the potential use of our genset is a quite challenging point. We are indeed in this moment, for example, following a CE marking procedure to facilitate the permitting aspect. At the same time, we also unfortunately faced some issues during last summer, and we had to cancel some demonstrations that were originally foreseen for the last summer. So our demonstration will take place in a music festival and construction sites. The music festival will be engaged by our team, and we already engaged some of them for the last summer, but unfortunately these events were fully cancelled, so we couldn't yet demonstrate the genset. Actually, of course, as we had some delays in the realization of the genset due to the lockdown of Italian partners, mostly because Linde, 3M, and Gemport and Rina too are Italian partners, we couldn't be able to have the genset ready for the summer, but the main issue was that we couldn't, unfortunately, have the events as well. The last main objective is, of course, as I said, the economical and environmental viability of our genset. I already expressed to you how the identified market is the short-term rental, but it is also relevant to highlight the fact that we already performed an LCA for our genset, thanks to VTT support, that highlighted how much is relevant the use of green hydrogen to make fully sustainable, to make really with an environmental added value our genset. I would like also to highlight that looking at the market, the relevance of green hydrogen is a key topic. Indeed, thanks to the project, we had the chance to interact with several stakeholders like Engie, like Puertos del Estado, like CGT Edilizia, but every time we interacted with them, one of the key points was, are you using green hydrogen? Is really a zero emission genset? So the matter of sustainability is really relevant, and we should target the use of green hydrogen for our genset to have a full environmental sustainable solution. So here in this slide, I recapped some challenges that I already mentioned in my speech. So the fact that these genset are, as I said, a sort of first of its kind. So at the end of the day, we didn't have any reference to develop a component like this. So we have been inspired by traditional diesel genset. The fact that end user require high reliability as the diesel one can guarantee to our genset, and also the fact that there are some permitting aspects that are currently difficult for put us in difficulties sometimes, for particularly for the use of our genset, as we are using pressurized hydrogen storage mostly in urban environment. Nevertheless, we let me say, we don't want to comply too much on this, but we are, as I said, working a lot on trying to make our solution ready for tomorrow. So not only ready for the demonstration of the project, as I said, we are collaborating a lot with stakeholders to analyze their wishes, needs, and also analyzing together how to overcome such barriers. To do so, we have also to think about how to exploit our genset. In this moment, as I said, the results of this project is a sort of the result of an orchestra work with many partners involved in the design and integration of both the pressurized hydrogen storage and the fuel cell power system. So it will be very important in the next months to decide who, for example, could be the exploitation partner. In this moment, the good stuff is that interacting with potential end user and interacting with relevant stakeholders, it is easy for us to understand what could be the market, how we could launch it there, and so on. So it is more in terms of exploitation understanding, let me say it is more an internal agreement than understanding if there is a market, because I can really confirm you that there is a very large market, and thanks also to our dissemination activity, we understood that initially not foreseen markets for us are very relevant. I can make you some example. Initially, we thought mostly to use of our genset in construction sites and temporary events, but we discovered that, for example, the movie industry is very interested in using zero noise and sustainable solution gensets, particularly because they have sets during the night in the center of the cities, in the middle of the cities, and they don't want to bother the inhabitants. And obviously because actors and movie industry is very keen to sustainability. Another sector that is a new stakeholder for us is, for example, the portual environment, that is more and more active and keen to look at the use of hydrogen in portual application. At this sense, we performed a lot of activities and interaction of stakeholders, even in this challenging period of COVID-19. I would like to thank you all, and I hope that you have enjoyed some pictures of our genset. Just for your information, we will release a brief video presentation of the genset within the end of this month on our website, so please take a look at it.
Thank you. Thank you very much, Stefano, for your presentation. I mean, I think it's great to see that the first gensets are finalized, as you've mentioned, and ready to be demonstrated in this year, and to see that you have reached so many stakeholders, especially end users, and those that were not, let's say, as you mentioned, originally planned. I think, as you said, the benefits are clear, displacing dirty and diesel generation by clean and silent gensets, especially on locations where there are people and inhabitants. So, Without further ado, I would like to pass the floor to Olli Himanen from VTT. He is the project coordinator of the InnoSoft project, and he will present the results of the trials and development of an innovative 50 kilowatt solid oxide fuel cell systems targeting commercial service sector applications. Olli, the floor is yours.
Thank you very much. So my name is Olli Himanen, and I'm the coordinator of this InnoSoft project. And as you heard, InnoSoft is an acronym for the development of innovative 50 kilowatt solid oxide fuel cell system and related value chain. InnoSoft project was started in 2015 and it was finished in October last year, so we are fully completed. InnoSoft project's total budget was 4 million euros, and the project partners were VTT, Elcogen and Convion from Finland, then Elringklinger and Research Center of Jülich from Germany, Enea from Italy, and Blue Terra Energy Experts from the Netherlands. The project had 3 main objectives. The first one was to design, manufacture and demonstrate a state-of-the-art 50 to 60 kilowatt solid oxide fuel cell system with 60% electrical efficiency and 4,000 euros per kilowatt cost level. The second objective was to demonstrate the system in 3,000 hours test run, and also to demonstrate the durability of the stacks in 10,000 hours separate stack test. And the third main objective was to identify and analyze the most promising end users and applications for this kind of technology. And the project, when it was formed, was based on the products of the industrial partners and motivated by their interest to further develop their products and services and consolidate an efficient value chain by a very close collaboration. Research centers supported these companies in their development, validation and demonstration activities. Then some examples of the project results. Elcogen has optimized their 3 kilowatt E3000 stacks for this InnoSoft system in terms of manufacturability, pressure losses and stack system interface. The durability of these stacks has been demonstrated in an ongoing stack test at VTT, and this test has already lasted more than 20,000 hours. And the voltage degradation rate has been below 0.5% per 1,000 hours. On the right hand side, you can see the average cell voltage of 2 different long-term tests. With orange color, you can see the situation before or in the very beginning of the InnoSoft project. At that time, the degradation rate was roughly 2% per 1,000 hours. And with blue color, you can see the average cell voltage of the ongoing stack test, showing or demonstrating a very nice improvement in the stack durability. Then example of the system development results. InnoSoft system has several highlights. It has a simple and robust design. There are no moving parts in the anode recirculation loop. There is no need for external water supply. And there is only one single and simple heat exchanger into the system. And altogether, Convion has been able to reduce the number of component count in the system by 67% compared to the reference system before InnoSoft. On the right-hand side, you can see the efficiency of the system with different stack technologies as a function of system power. And Convion has reached 57% electrical efficiency with electrolyte supported stacks in the previous systems, and now they claim to reach up to 63% peak efficiency with Elcogen's anode supported stacks, and Convion sees that there is still room for further improvement, so that with further system optimization they could even reach 67% electrical efficiency with Elcogen stacks. Higher total efficiency can be reached by utilizing a heat recovery system, which will add 50 to 20% to these numbers, so that the total efficiency will be above 80%. And now Convion says that the customer interest is increasing rapidly, especially in Asia and in Europe. And they are now forming partnerships on the selected key markets, and they are also increasing the production capacity to meet the market needs. Then example of the system demonstration. This Inosoft system is being demonstrated in Lempäälä in Finland as a part of a hybrid microgrid, which can be seen in the picture below. This microgrid has batteries for frequency regulation and load shifting. There is a megawatt level PV power plant, then biogas fueled gensets, and 2 Convion systems fueled with biogas. First C60 system has been in continuous operation since June this year, and the second system will be delivered by the end of this year. These 2 Convion or Inosoft systems, they will be used in DC power producing mode with a total DC output of 130 kilowatts. Then what kind of risks we have faced and what we have learned. First, the system design and manufacturing took much more time than expected due to several reasons. One was that the Convion needed to redesign the frame of the system. This was changed from a separate pipe frame to a self-supported sheet metal structure, and this was needed to meet the ambitious cost target. And the second reason was that Convion wanted to implement learnings from the ongoing Demosoft project into this Inosoft system. And altogether, the project duration was extended by 14 months. Then exploitation and impacts. Industrial partners, they have improved and demonstrated their products, services, and developed an efficient supply chain. And these will be utilized or have already been utilized in their businesses. And the research partners, they have improved their experimental facilities and know-how related to solid oxide technology, so that they can now have a wider and deeper support for companies and public sector working in this field. And then impacts of the project. We have now a strong European value chain for solid oxide systems from single cells and interconnect plates to stacks and complete systems. We have been able to design and demonstrate a solid oxide fuel cell system with very high efficiency, and we have been able to integrate knowledge from other EU projects, for example NELHI, DemoSoft and QSoft. Then more impact examples. This one is from Elcogen point of view. Positive results from InnoSoft and QSoft projects. They have enabled Elcogen to sign a 12 million euros quasi-equity loan from a European investment bank for further research and development. And the goal of this financing is to aid in the setup of a new factory for single cells and stacks used in solid oxide systems, and this will create highly skilled local jobs related to this process. The target capacity of this new factory is 50 megawatts annual production, and it will be located in Estonia, in Tallinn. Picture below shows the timeline for this factory project, and right now Elcogen is validating manufacturing equipments, and they have an ambitious target to have factory ready and full-scale production ready within 2 years, in the second half of 2022. Then more impact examples. This one is related to improvement of conveyor system technology. And here you can see the improvement of 5 different key parameters related to conveyor system. And if on the left-hand side you can see the, let's say, reference unit from 2012 before the InnoSoft project, and on the right-hand side is the other parameters related to the InnoSoft system. And you can see that the balance of plant cost, number of functional components, number of instrumentation, and weight to power ratio, all these have decreased by roughly 70%. And volume to power ratio has decreased almost 90% when comparing to the reference unit. So a very significant improvement in all these key aspects. Results of the project have been disseminated in different workshops and conferences. We have had 20 presentations. Then during the project duration, we had 3 press releases. We have organized 2 workshops and have had several presentations in conferences. Results have been published in 5 scientific articles. There are public deliverables on the project webpage, and we have also made a promotional educational video which can be found from the YouTube. Then this project has had lots of interactions with EU projects, for example NELHI on single cell and stack development, DemoSoft on system design, manufacturing and operational experience, then QSoft on quality related issues on stacks and stack components, and then on Marie Curie project HALE-STACK also on single cell and stack development. Then we have also had lots of national and international level interaction with for example, Finnish-German project STEP, IEA Annex, on information exchange and also with ERA. I hereby thank you very much, EU for funding and Project Officer Dionysis Chimis for the very good collaboration. Thank you.
Thank you. Thank you very much, Oli, for sharing the results of the project. I mean, it's great to see how the project has built actually on a number of research activities, some of them funded by us, and to see the improvements achieved. And also great to see the additional leverage of funding, especially on the manufacturing capacity located in Europe, which is what we were referring earlier on today. And the great potential, I mean, power efficiencies in the order of large CCGT plants. And I think that's quite impressive, and especially looking at the size of the system, and this is done without pollutant emissions. So thank you very much. And now I will ask all presenters to put their cameras on, if that's okay with you, as we will move to the question and answer session. And I will start with Mr. Andreas Frommer, with Andreas. There is a question that, I mean, right now these units, as you mentioned, are running on natural gas. And is there anyone that is running on hydrogen with the storage right now in combination of renewable energy sources? This is a question that comes from the audience. And I think I would like to use this one so that you can also tell us how do you see the role of micro cogeneration with fuel cells in the future, especially as we have more and more renewable gases in the system. So do we have any units in place running on hydrogen and with the storage? And in the wider perspective, how do you see the role of these units in a renewable gas scenario?
Yeah. Thank you, Antonio, and thank you for the question. We are focusing on the first phase of rollout, the commercialization, and therefore it is more market-orientated than orientated on the probabilities of the technology. Because the technology would work with hydrogen, at least we have hydrogen within the stack, but relative to the market, there's no demand for units running on hydrogen, on pure hydrogen right now. We will have a transition period where we have, I would say, up to 30% hydrogen within the gas grid. And that's something we are preparing for, all OEMs at least. And in parallel to that, we are working on pure hydrogen fuel cells, but more in the long term or mid-term, you could also say, depending on your fuel, to be ready once we have either pure hydrogen within a distribution grid. There are areas in Leeds, for instance, and of course there are fuel cells available for that, but not commercial wise. And this is one direction, and the other direction is to have a combination of electrolyzer and fuel cells with storage between. And then the view is more in the direction to have those units in quarters, in an area with several houses, probably also with some commercial buildings in addition, and then have a combination of all technologies: fuel cells, heat pumps, PV, storage, electrolyzer, and so on.
Thank you, Andrea. There is another question for you, which goes into how the units are operated. I mean, you've mentioned before some customers have replaced their heating systems with these micro CHP fuel cell units. Does it mean that the fuel cells are partly operated as heat only? I mean, not electrical production. Is that an operating mode? And what would be the efficiency in such mode?
Thank you. So it's a combined heat and power, and that's the benefit to reach this high efficiency. We have also units in the portfolio of PACE more focusing on the power production, because this is the core benefit, providing the return on investment. But relative to the sustainability, the combination of heat and power is key. And therefore, the units mostly running heat-driven. So we need demand for the heat to have the power production at the same time. And the sizing of the units over the years was step by step, it came to the result that for a single family house, 750 watt would be the perfect match to the load profile of a single family house. And you have seen units with a higher capacity for electrical power, 1.5 kilowatt, and this is more in the direction for small commercial buildings or residential buildings with an electrical car to be fueled by power, you can say. Then the balance between power and heat is more in the direction of the power.
Mm-hmm. Thank you very much. And final question for you in this first round: is the system also efficiency for space cooling? Can it be used for providing space cooling? They are asking.
Yeah, there are two ways, at least for the fuel cell itself. There are two ways. One is to use the power produced on site, and then using the typical cooling systems, electrical cooling systems. Second is to use absorption or adsorption chiller, but based on my knowledge, for this size, it is not commercially available. It's too small. It starts with several kilowatts. Mm. So you have to convert the thermal power into the heat into cooling with an adsorption or absorption chiller, and for such, if you want to have that commercially available and to affordable price, I think you have to go in several kilowatts.
Mm-hmm. Thank you so much, Andreas. I will move now to Stefano with a number of questions. There is a question that has been made in relation to the electric power that you can generate out of a 10-feet container. I'm not sure if you mentioned this 10-feet container. Otherwise, you can relate to the power and the container sizes of the gensets that you have in the project.
Yeah, the container size is the same for both the 25 and the 100 kilowatt genset. So we are aiming to realize 4 25 kilowatt and 4 100 kilowatt genset. And both of them are stored for a matter of practicity in a 10-feet container.
Okay, perfect.
So maybe the 25 one could require a little bit less space, but as you know, it's easier to transport, etc.
Mm-hmm. Okay. And there was also a question in terms of the points you made about the interest of end users in relation to green hydrogen.
Yeah.
Now, how are you dealing with that? I mean, you have reached a number of end users, music festivals, as well film industry, and they point out to the fact that they wanted to see green hydrogen being used. How does it relate to the hydrogen logistics that you are looking at in the project, and how are you basically addressing that, or intend to address it in the project to build a supply chain around hydrogen first, and second, green hydrogen?
Well, generally speaking, you have to consider that we have the opportunity to have with us on board INDE, that has a quite capillary presence all around Europe, so they can supply hydrogen really in a lot of places in Europe. Obviously, we are not always talking about green hydrogen. We have to be frank. We, for example, discussed about this point with some festival, for example, and the festivals were okay to have a green hydrogen supply that could be a little bit more expensive. But you have to consider that at the end of the day, the cost of the fuel is only something like the 10% of the full cost of a short-term rental, because at the end of the day, the trickiest point is, shipping the genset, installing it, etc. So if we have even an extra cost on green hydrogen, if compared to on the market hydrogen, so blue or gray one, this is something that is manageable by, let me say, particularly temporary events who are more focused on these sustainability aspects. But also from the construction sector, we found an interest for the use of green hydrogen. Regarding developing a local value chains, of course, what we are looking at is every time we interact, for example, with a festival, for example, we look around if there could be some local producer. For example, in the case of Wacken Festival, which is a festival hosted in the north of Germany, we were in contact, thanks to Wacken, to a local electrolysis plant. It was a German-funded project installation that realized, let me say, not a wide production of green hydrogen, but also to make a connection with this project, we were in contact with them to, valorize the locally green hydrogen that was produced exploiting a local wind power production.
Mm-hmm. Okay. Great, thank you for those links that you've shown in terms of the local green hydrogen production and the gensets, actually the hydrogen used. Now, you've mentioned now some specific names on end users, and the solutions you are developing are looking at substituting diesel generator. I mean, of course, price-wise, we can expect the gensets to be still, the hydrogen gensets to be still more expensive than the diesel generation. If we look at in terms of the capex, we have heard about the benefits. So my question is, what type of propositions is the project exploring or intend to explore when it becomes to offering those solutions to the end users? I mean, how do you can go about entering the market? Which type of business models do you have in mind to explore and to convince basically those that will ultimately adopt the solutions?
Well, the main idea should be to first interact with rental companies who already have a sort of green genset fleet. I make you an example. CGT Edilizia is the largest Italian rental provider. It is a subsidiary of Caterpillar. And they already have a sort of green line where they rent mostly diesel hybridized with battery. What we, interacting with them, we understood that they could be interested to purchase some gensets and, open this new fleet. At their side, the most scaling point is, of course, the availability of an easy refueling logistic, because in this moment their main issue is not at the end the capex, because if we can achieve something, as I said, around 2,500 euro per kilowatt, even if it is something like 5 times the genset capex, they are quite glad and keen to have it in their fleet, because at the end the capex is not a relevant percentage in their cost of rental. But the main issue for them is the facility, the easiness of finding hydrogen and refuel it more or less everywhere. In this moment, this is the main blocking point for us, to be honest with you, because the risk is that, okay, I can provide the genset, but then to supply hydrogen at the site, I could have a lot of cost. Also because you have to consider that it's for permitting aspects, it's difficult to have large storage authorized, okay, particularly for temporary events. So I cannot have, I don't know, a storage for 1 month, a pressurized hydrogen storage for 1 month authorized in an area, because at the end, I have to minimize the pressurized and the flammable and explosive presence of hydrogen in a inhabited or crowded area. Therefore, particularly this point is scaring the end user. But from the business model point of view, what we are looking at is more than developing a new or for example, we can consider that one of our partners could be the official reseller, but of course the main customers will be or rental companies or energy utility that provide temporary power to events, etc., like, for example, Engie, with whom we are in constant contact.
Thank you, Stefano. And actually, there was a question which comes well now, because you talk about the permitting procedures.
Yeah.
And it related to if you have any experiences to share, because of course those gensets that you've mentioned, they will require from hydrogen on site. They will be installed in areas where there will be relatively quite amount of people thinking about the music festival, other temporary events. What are your experience, and do you think there is still some work needed in there to make this easier, to do some awareness raising to those granting these permissions?
Well, for sure, what we should increase is the awareness of local fire department, because at the end of the day, the permitting for events always pass through the tables of local fire department. So the permitting authority is always, even for traditional diesel genset, is always by local fire department, because once you have a fuel in a crowded area, you have to receive the go from the local fire department, more or less in every European country. At this topic, at this purpose, the main issue is that as there is no existing normative on hydrogen fuel at genset, unfortunately, then the habit could be something like, okay, I'm scared, okay, because I don't know so much about it. This could be an issue, I don't have a rule and a precise regulatory framework to refer to, etc. So at this framework, what we are doing is the following: to for sure make the genset box, so not the storage box, as much similar and as much regulated as possible like diesel genset. So for example, we started this CE marking approach because at the end, if we can say that the electric box is like a traditional genset, this can facilitate a lot. Then it will be a matter of understanding how and where to put the hydrogen storage. That, as you can imagine, is the main issue.
Thank you. Thank you very much, Stefano. I mean, you mentioned firefighters, just to bring to the audience attention that we actually did have a project that was precisely doing that, and which was training firefighters on hydrogen aspects and how to react to any potential incident. So thank you so much, Stefano. And maybe I use this chance that if any interested member of the audience is interested to maybe demonstrate some of the gensets, they should get in touch with you through your project website. I believe.
Exactly. Yes, there is a form. You can easily contact me. The demonstration campaign has been postponed, so we are again looking for demo sites, particularly starting from summer 2021.
Okay. Brilliant. Thank you. Thank you again, Stefano. Now I will move to Olli now. We have a number of questions which I will try to organize. The first one comes and is asking about how did you manage to improve the stack durability within the project? How did you do that? What did you look into? What was the means to get there?
I think there were several things we did. Optimization of materials, then material composition, material, let's say, other parameters like thicknesses, optimized cell structure and cell materials from the Elcogen AS in Estonia, then new protective coatings, that kind of things, further optimization of let's say already existing solutions.
Okay. Thank you. And related to that, somehow you mentioned that there is still potential for improvements in relation to the system efficiency, or to the efficiencies, could be also a stack. Is this something that is valued by the customer? I mean, is this room for further improvement something that could be driven by what the customers are asking? Or do you think they would prefer to focus on, okay, let's have better lifetime and more cost-effective or cheaper system? What is your view on that? Where are we heading?
I think that cost-related thing, that is maybe the most important one. But for example, in the case of for example, wastewater treatment plants, they would like to have as much electricity as possible, as they already have excess heat available. So in that kind of applications, high electrical efficiency is really appreciated. But as you said, I would say that the minimizing costs by mass production is the key.
Mm-hmm. Okay. And what are the, if you want, the theoretic limits of power efficiencies a member of the audience is doing? I mean, do we have any limits with the layout of the InnoSoft unit that we can reach on power efficiencies?
Very good question. I think that this 67% is what Convion has claimed with the Elcogen anode supported cells as such, and with further system optimization. I think that of course there is still room for further optimization, but there is a risk that it will increase costs. For example, there can be thicker, for example, thicker insulation materials to minimize heat losses, or there can be thicker cables or more expensive power electronics to boost the efficiency, but it's also that will increase costs. I think this is what Convion has thought, that this would be the, let's say, optimal and with reasonable costs.
So again, a trade-off, I can understand from those things. And moving a bit now to the manufacturing side, if you want, what is the lead time for the delivery of such a second generation system? I don't know if you can answer. So what would be, if now I would like to get one of those systems, what would be the lead time to get it installed? I guess it's a tricky one, but...
Yeah, I think currently Convion's production is fully sold out with other demonstration projects. I think that's something I cannot now answer. I think that if you are going to buy one, I think then it's better to contact Convion directly, call to Erkko Fontel.
Yeah, I mean,
but I would say that maybe roughly half a year or something like that.
Okay. I mean, that's linked to some extent to another questions we just had now, which is about what's the current capabilities of Convion and what is the room for increasing those in the future. You've mentioned about the manufacturing facility on the Elcogen site, which is looking at the stacks. So, and you've mentioned, I think, briefly a bit also on the intentions to scale up production volumes on Convion. I don't know if you can elaborate a bit on that one as well.
Yeah, I think currently, or the Convion's strategy is that they try to outsource as much as possible of the production, so that they do the final assembly by themselves, so that they get, for example, lots of components like reformers and other heat exchangers and that kind of modules ready, and then they will do the final assembly by themselves. And I think in this way they can of course increase the or they can look for larger subcontracting to increase the volume, but I think currently what is limiting is the final assembly, which they do by themselves. I think that's something I think maybe they will look in the future how to also maybe outsource part of the final assembly, or how to increase the capacity of that.
And how I mean, now we were talking about the Elcogen stacks. I mean, how easy would be to change the stacks? I'm thinking now if we have more stacks manufacturer players and there is more competition out there, how flexible would be the units to be able to include the stacks from other providers? Is that something that could be possible without many or much changes in the design?
Yeah, Convion says, or when the InnoSoft system was designed, it was done so that it is flexible with the stacks, so that the whole system doesn't need to be redesigned. But because they already have experience on anode supported stacks and electrolyte supported stacks, they say that it shouldn't be a big deal to use also other stacks. so that it's flexible and also risk mitigation in that sense also.
Okay, and a final question for you. It concerns the feedback that you may have had from the operator of the unit in Lemene in the Finnish demonstration project. I don't know if you could elaborate a little bit more on what this smart grid. I read before in your presentation it was something with injecting heat and as well in a district heating network. So if you could elaborate a bit more on what type of system this unit is being used for, and also if there are some feedbacks already, if there are some efficiencies measures in there that could relate to the values that you've mentioned. So what is the situation with this project?
Yes, as said, in Lempäälä project, it is a hybrid microgrid where two Convion systems, they are used to provide DC power to separate DC network and also heat to local district heating network. Currently there is one system in operation, and when I talked with Convion, they said that they will, let's say, release the data of or operational experiences when they also have the second system up and running. Mm-hmm. So they would like to wait a few more months to publish publish the data.
Mm-hmm. Perfect. Thank you. Thanks a lot, Olli.
Thank you.
In the meantime, there was a question back to Andreas. Was a question that came for the micro CHP applications. I mean, some years ago, we people were familiar with the NFIL projects where we were having, if you want, a small scale field trials with 100 type of units installed by different manufacturers to validate the performance of the units, to show that they were working. Now we moved into volumes, in particular in the PACE project. The idea is also to give confidence to manufacturers to scale up production so that they can benefit from the economies of scale, if you want, on production side, more manufacturing that is more and more automated. So where are we with that? I mean, where are European actors in relation to production of large quantities? If you could comment a little bit on that.
Yeah, of course, I can do that. There are two things. One is in the direction of the manufacturer itself. So the manufacturer are able to make the next huge step, because the aim is to have 500 units manufactured by every OEM, allow him to have automated processes within the facilities, enlarge them to be able to produce more than 1,500 units per year. So all these things for this step necessary to step from a pure handmade manufacturing for some small demonstration towards an industrial manufacturing process. That's the key. To step up with the supply chain to such numbers. And on the other hand, with a view to the market, we have different directions to establish new roads towards the end customer, together with installers, together with retailers, looking on market access in different regions in Europe, and also see the differences, not only relative to installers and to heating companies, or also to online platforms, as well as looking on the different regulations, favorable or non-favorable, in the different member states, to compare them, and also to have recommendations out of this for the future.
Mm-hmm. And this question was followed up by, we've seen that there are quite some number of units in Germany. Some other markets like Belgium also are getting more and more units. But why? I mean, why Germany and not other countries? What is needed to see this technology mainstreaming as well in other countries, micro CHP fuel cells?
Yes, of course you need some demand for the heat. So I think there's less demand in the south of Europe than in the north, because we are talking about combined heat and power, and not a pure power production. But you are talking more in the direction of regulation, and that's truly the case. So we have a supportive regulation in Germany relative to produced power out of CHP solutions, exactly to support this combined heat and power to have the highest possible efficiency of using the primary energy, and that's key to reduce the CO2 emissions. And then we have also a favorable policy in place, for instance, also in Belgium, supporting such units.
Mm-hmm. Thank you. Before I move to a general question to all of you, I wanted to ask you, Olli, a question that came now, which is very interesting because it talks about whether you have or whether there are plans to improve our density. But the underpinning message there is really in terms of fitting applications for heavy duty. I mean, we think about maritime here, which is now a sector where a lot of the people are putting a lot of emphasis because it's hard to decarbonize. So what could be the role? I mean, are you looking at using these stationary fuel cells for maritime applications like main propulsions? And is work going in this direction? What's your opinion?
I think that this solid oxide technology itself, I think it can be utilized in maritime applications, especially when there is LNG as a fuel, then it has benefits.
Mm-hmm. So it could also be not only LNG, it could also be ammonia.
Yes.
The fuel by ammonia could also be a very interesting direction.
Mm-hmm. Okay. So we have a few minutes left, so I would like to ask you one question to all of you to close this session. If you were to come here again in a year ago, where would you see your project being? I mean, what could you tell us in a year if everything was going according to plan? So I will give first the floor to Andrea. In 1 minute, each of you, where do you think the project would be at in 1 year? I know it's difficult to say, but what would be your aspiration and desire? So Andrea, 1 minute for you. Thank you.
I would say it's easy. in 1 year from now, we would install all the units, sold and installed all the units planned for base, which are more than 2,800. Probably we would have more. And we will have them in operation, providing data for monitoring and also to see the efficiency, the impact is for the energy transition in Europe. So we will be in the final phase of the project, a very successful project.
Thank you. Thank you so much, Andreas. Stefano, what about you?
Well, I hope first that we will be able to report the use of the gensets in some music festival events, because this would mean probably that also this COVID-19 wave has no major impacts on all our lives, because we really hope to see some concert again, better if with our everywhere genset, of course. But generally speaking, my goal would be to have the 8 genset ready, and if possible, of course, already tested. But I really hope to showcase next year this. Last year I answered to showcase the first genset. More or less, we arrived there because we couldn't test, but we achieved the fact to have the genset ready.
Thank you, Stefano. And Olli, I know Innosoft has finished now, but there are activities that continue. So where could we be in 1 year?
I hope that within 1 year, Elcogen's stack factory or cell and stack factory project is progressing according to the schedule, so that they will reach the full production in 2 years from now on. Then I really hope that the Lempäälä project is progressing well, and within 1 year we will have Convion and Elcogen have been able to publish a nice data of two systems, maybe world record efficiency and small degradation rate and that kind of things, and also that the Convion and Elcogen have lots of customer projects, customer deliveries, and that all the other project partners also, they have utilized the results of the Innosoft project in the businesses and research activities.
Great prospects, I have to say, across the three projects. And I have just 1 minute left to really thank you, all of you, for your contributions, for taking the time to prepare the presentations and for being here. And thank you to the audience as well. Great participation, a lot of questions and answers. Hope we answer most of them. And as I said, do not hesitate to get in touch with these projects. Some of them, actually I would say all of them, will offer opportunities if you are interested in using some of these technologies. So get in touch with them, get in touch with us. And yeah, do not forget to follow the next session if you are interested to hear a little bit the underpinning research that has brought us here as well. That will be at 11 o'clock, session moderated by my colleague Dionysis Simis. And this is it. Thank you very much. I would like to close this session again. Thank you very much, Andreas, Stefano, and Olli. And yeah, we will see you soon. And everyone, stay safe. Thank you. Thank you so much.
Thank you.
All the best.
Bye-bye.
Thanks also to this audiovisual support. Thank you.
Indeed. Thank you to them. Thank you.
The Energy Observer crew is sailing around the globe to raise awareness about climate change, advocating for renewable energies and hydrogen. Those I've met in Japan and Europe say hydrogen is very useful indeed. I wonder why it isn't more largely available. And what kind of future will hydrogen bring us? Continuing my journey in Nantes, France, I met with CNRS researcher and university professor Olivier Joubert. He is among the top French researchers on hydrogen. He might just be the right person to talk to understand what's ahead of us. Does hydrogen have a promising future? He was enthusiastic to answer.
Les activités de recherche tournent autour de la production d'hydrogène, notamment par électrolyse à haute température, ou bien la conversion de l'hydrogène en électricité grâce aux piles à combustible fonctionnant à haute température.
My first question was about hydrogen production. There's green hydrogen, but also blue, gray.
L'hydrogène n'a pas de couleur, d'accord ? C'est un gaz inodore et incolore. Mais l'hydrogène vert, ce serait l'hydrogène qui serait produit à partir d'électricité et de l'électrolyse avec de l'électricité verte.
So hydrogen, what is going to happen in the next few years?
On peut, d'ici une quinzaine d'années, avoir de nombreux usages à base d'hydrogène. Au niveau des projets, je pense qu'on pourrait avoir tout ce qui est actuellement thermique pour être transformé en électrique avec pile à combustible ou batterie. Ou l'hybridation, c'est-à-dire quelque chose qui emporterait à la fois des batteries et de l'hydrogène. Et bien sûr, la recherche sera là pour mettre en place des innovations qui constitueront donc la pile à combustible du futur, qui sera peut-être moins chère et puis qui aura une longévité plus importante. Donc ça, c'est un peu le futur.
Thinking of what I'd seen at the Fukushima plant, I asked him if hydrogen could change cities. He talked about large-scale experiments, hydrogen cities in Japan, for instance, where houses use hydrogen and produce their own electricity. But even here in Europe, things have started moving.
Les initiatives les plus marquantes, quand on regarde autour de nous, sont les stations-service. Et donc, quand on sait déjà qu'il y a à peu près une centaine de stations-service, ne serait-ce qu'en Europe, c'est déjà beaucoup. Mais je pense que ce qui est plus remarquable, ce sont les flottes de taxis à Paris. La flotte Hype, avec 120 taxis, et qu'il y a déjà plusieurs véhicules qui sont déjà arrivés en bout de vie, et qu'il faut changer. Et là, je crois que c'est quelque chose de vraiment remarquable.
Hype taxis are a handy way to move around Paris with zero emissions. I hopped in one on my way to the next leg of my journey.
Ça fait 4 ans et demi que je conduis des voitures à hydrogène et j'ai choisi de passer à ce modèle-là parce que je pense que tout le monde doit, tant qu'à travailler dans les mêmes conditions, opter pour le moyen le plus respectueux de l'environnement. J'ai choisi de travailler conduisant une voiture à hydrogène parce que c'est une solution qui me permettait moi d'avoir la conscience plus tranquille en travaillant dans les mêmes conditions qu'avant. On apporte notre petite pierre à l'édifice en tant que chauffeur dans une filière qui, je pense, et j'en ai l'intime conviction, va finir par devenir une solution qui aura toute sa place dans la société du futur. Et en plus, là, on est parmi les premiers à conduire des voitures à hydrogène, donc on pourra dire dans quelques années à mes enfants, à mes petits-enfants, avec un peu de fierté, je pense que j'ai été parmi les premiers à conduire des voitures à hydrogène.
The idea of setting the example resonated with me. I really wanted to see if hydrogen could power a city or even a country, Is there somewhere where people are doing just that? Scotland, all the way north to the Orkney Islands. There is more to this spectacular landscape than meets the eye. Here in Orkney, people have built the Energy Lab of the future. A real-life experiment, an archipelago powered by renewable energies.
I'm the Managing Director of EMEC, which is the European Marine Energy Centre, and we're based here in Orkney at 59 degrees north.
Neil Kermody has implemented programs on these islands, relying a lot on hydrogen.
The advantage of using hydrogen is it's extremely flexible. It can provide heat, it can provide motive power, and it can provide electricity. The most impressive achievement we've had so far has been that time when we took tidal energy and made hydrogen. And that's the first time anybody had ever done that anywhere in the world.
The Orkney Islands are now famous because of it. Adel Liederdale used to work for the City Council of the islands and has overseen the implementation of a new energy model.
I am the Hydrogen Project Manager at the European Marine Energy Centre.
She's now joined EMEC and is uniquely able to tell us what happened here.
Orkney began innovating around hydrogen due to a set of circumstances we had that stopped us from putting electricity into our local grid. So here at EMEC we are the world's first and only fully accredited tidal energy test centre. We had another world first in generating green hydrogen from renewable energy. We're using that green hydrogen in things like powering ferries, planes, cars and heating systems.
Oh, and we're using it for vehicles. So a great number of different projects, and we think we've only just scratched the surface. There's a lot more we can do with hydrogen.
There's something quite different here. They've tried it and it works at a large scale. But they're also doing it with such a positive mindset. They want to see change.
So I would very much like to see that renewables and hydrogen in every household, not just in Orkney but throughout the world. We would really like to see that renewables play a part in everybody's lives and we continue to tackle climate change.
The thing is that what we've done here can be done elsewhere. We've taken the energy that we've got in the tides and the wind, but it could be solar, it could be anything else. But by making hydrogen, you get flexibility in your energy system. And that's something that anybody can do. I want to see a future where we're not burning fossil fuels anymore. I really believe that hydrogen is a key part of making that all work. It can actually displace so many of the things that we presently do with fossil fuels. Hydrogen can do this, and it can do it now.
I think this is the proof I needed. Hydrogen can power a brighter, more sustainable future. And it can work now. It's almost unbelievable. It works so naturally here in Orkney. I started with a question, what is hydrogen? And now I can't understand why hydrogen isn't more ubiquitous. It should be everywhere. Activists and governments, industries and citizens, we all share a common goal. We need an energy transition, a more suitable model. This is our biggest challenge. But the solutions are here, right at our fingertips. It's our call, it's our responsibility. All these people, those I met and many others, are the faces of change. They are working for you to see that it's possible, that we can become the champions that defeat climate change.
Okay, hello everyone and welcome back. We'll be continuing with fuel cells for stationary applications, but in this session we'll be focusing on the next generation of products, focusing on low TRL research projects, really the underpinning research that enables the demonstration projects that you saw in the previous session that was moderated by my colleague Antonio Aguiló. So my name is Yanis Timis. I'm a project officer at the FCHGU, and I'll be moderating this session. And with respect to the structure, we will be listening to 4 presentations from different projects. And we do encourage you to use the Mentimeter, the Q&A functionality as much as possible, which will allow you to interact with our speakers. And we'll be taking these questions and answers at the end of the session, after all 4 presenters have finished. So we can start with the first presentation, which is from Project Cell3Dtor. It's really a one-of-a-kind project. It's really out there. And I invite Alberto Arancon to walk us through what they have achieved.
Okay,
Alberto,
good morning. Okay, thank you very much. And good morning, Dionysis. It's a pleasure to be here again, because this is the second time we present the project. This is the final report of our project. So, yes, if we start with the presentation. Yeah, well, first of all, the Cell Editor project. Sorry, I have some technical things. Okay, no, it's fine. So the Cell Editor project is under the call topic. Well, next slide, please. Okay, the Cell Editor project is under the call topic on development of cost-effective manufacturing of fuel cells, and this was funded in 2016. Okay, sorry about that, and it's already finished. Okay, so the total contribution from the European Commission was to more than 2 million euros, and it was a very nice project crossing in diagonal the entire Europe from Sweden to the Canary Islands. Next slide, please. The main goal of this project was to develop a new technology for manufacturing SOFC parts and stacks based on 3D printing. And of course, the idea was to develop the whole thing, because we started from scratch. So the idea was to develop the printable inks and slurries, also the printer, a multi-material ceramic 3D printer, able to print all these devices. Also, it was important to include into the project the whole manufacturing process, not just the printing, but also the sintering. And finally, the idea was to be able to test the enhancement achieved with these 3D printed parts. Okay, we basically, when we try to compare with the state of the art, it's very easy, because there was no state of the art. So basically, there were few trials in few labs, but any big project before was specifically dealing with this, and we are very happy, as you will see, with the final results we obtained. The main idea of the project is that you can start with a design that even you can generate by any of the fancy design software that you have available. You can even simulate it using finite elements or other type of simulation strategies. And then when you have all this, you convert it into a file that is printable, no? And then this printable file is basically a series of layers that one after the other will generate a part or the complete stack. And then afterwards, we have to make a final step, that is a sintering step, to remove all the organics introduced in the printing process. No? And all in all, the idea is to have some advantages due to the 3D printing strategy. So it's not just generating conventional technology, but introducing some complex geometries, or for instance, self-supported stacks that give you an advantage. The application and market area was at the beginning focused on a highly heterogeneous sector as is the residential. Okay, and the selected target is Europe. Next slide, please. Well, if we go step by step on the achievements of this project, well, the first, as I mentioned to you, was to generate a family of printable functional materials. Specifically, ceramics is something very rare in the field of printing. Basically, what we have available are plastics, but not ceramics, and not functional ceramics at all. And during this project, we were able to develop at an industrial level slurries for all the important materials in SOFC, SOEC. So we were able to generate nickel oxide YSZ pastes, LSM YSZ pastes, YSZ pastes, but also a thing that represented a solution, a strategy that was a sacrificial material. There was a simple polymer that during the sintering step will be removed, and then will give behind him as an open space. So it's good for the developing channels and other elements for the 3D printing, 3D printed cell. Okay. So next slide, please. The next achievement was to develop the printer itself. No, this was very important. We started from an already commercial industrial 3D printer for ceramics, but it was a single material 3D printer. And at the end of the project, we reached a multi-material 3D printer. No? It's the one you see in the picture on the left, and it's able to print very big sizes. So 20 by 20 by 10, so it's a big piece. And currently, after the modification of the hardware and software, we are able to deposit by SLA the electrolyte, the YSZ, and then for other materials by means of robocasting. And in the video that is in the next, activating the next slide, you see how this machine works. Okay. Oops. Sorry, can you come back to the video, please? Here, okay. The video, can you activate the video on the right? Sorry, is it working? I cannot see it in my screen.
I don't believe it's working yet. They are making an effort to,
okay,
now it's on.
Great. Thank you very much. Thank you very much. So here you see our facilities and our lab, and you will see automatically exactly the machine I was talking about. This machine is based on an SLA system that is basically a doctor blade, like you see, that is able to spread the YSZ slurry. Then with a laser, you are able to cure and harden parts of this according to the file you introduced before. Okay, and then you can even introduce at a certain moment some laser machining in case you want to fabricate some holes specifically for your 3D printed structure. And then when you have this hardened, you go for another layer of the same material, or even a layer of a different material. And now here you see how this robocasting arm that is able to introduce 4 extra materials in the printing process is starting to print. No? And then afterwards you cure also this material and you start. And once and again, repeating this process, you are able to generate a layer by layer printed part that can be as high as 10 centimeters, as I told you before. No? And well, let me finish with the video, because then you see that we are very funny sometimes also. Okay, so next slide, please. After developing the 3D printer, the idea was to be able to control the whole process. As I told you before, it's not just a matter of the machine, it's a matter of the process, the manufacturing process. And we were able to combine all the different materials required, starting from the YSZ and then put it on top the nickel YSZ or the LSM YSZ, so the cathodes and the anodes. But also on the left side, you see how we were able to fabricate some channels by using this sacrificial material I mentioned you before, no? The one that was removed during the sintering and the binding process. No? If we activate the video on the right, okay, you will have a clear view on the fabrication of one of these small cells. Okay, so we start with the SLA, and then we fabricate a certain roughness in order to ensure the attachment between the layers, okay, by doing a certain laser milling. And when this is finished, we have this rough circle here, okay, and then we come back with the second method, the printing, and the robocasting printing, and then we introduce the second material, in this case LSM-YSZ. And with this, we finish with the platform fully printed, okay? Next, please. Okay, so after printing, so developing the feedstock, developing the printer, then developing the process, and finally the idea was to develop the sintering step. This is one of the key aspects of the project, because at the end we want to print all parts, and this is fine, then we can optimize the thermal treatment independently, but also the idea was to be able to develop multi-material parts, no? And in this case you have to be able to print all together and then sinter all together, and there was the need for finding a trade-off between the densification, the required densification of the electrolyte, and avoiding this extreme densification in the electrodes. No, we were able then to find this trade-off at 1250 degrees C for the sintering of the Y set, and everything. We kept all the functionalities, and then a high density of the electrolyte as required, and then we applied the anode and the cathode on both sides. And I have to say that we obtained, in the case of the anode, very good results, so comparable to the literature. And in the case of the cathode, we experienced some problems, not depositing, but with a final performance that was a little bit below the expected. You will see now. Next slide, please. And then about the enhancement achieved using this printing strategy. Let me explain a couple of examples. We have a few more, but these two I think that are very interesting. On the left side, you see that we were able to simply corrugate the electrolyte, and this is absolutely impossible with traditional manufacturing. And just by corrugating the electrolyte in an electrolyte-supported cell, we were able to increase in 60% using conventional materials the power performance, the power density achieved at the end. And this 60% is straightforwardly correlating with the increase in area. So this is a very simple but important strategy from our point of view. Even we degraded for 700 hours, keeping the expected low degradation. No? I mean, we were using state-of-the-art materials, but with the printing, we didn't introduce any new thing that alter the long-term behavior. And on the right, what you can see is a fully printed SOFC cell. Okay, this is fully printed, so from the beginning until the end in a single step. And you can see in the SEM cross section that we experience some problems in reaching a porous LSM-Y set layer, but in general the macrostructure looked pretty well. And then we did some measurements, and what we observed was that we obtained around a little bit less than 100 milliwatts per square centimeter, which is not the expected, should be around 200. I mean, according to the thickness and the temperature for the measurement. But still, it's the first time ever that an SOFC cell is fully printed. So in this sense, we are very happy. Okay, next slide, please. We faced few problems during the project, as expected, of course, because we started from scratch. I'm not going to mention all of them, but probably let me say that the first problem we faced is that some of the materials we were using were absorbing UV light. That was the one used for curing, and then for them we had to choose completely to a photothermal curing strategy. Also, was very interesting the difficulties we experienced in developing certain 3D structures, and how we introduced this sacrificial material that was completely new also and not expected in the project proposal, but that gave us the opportunity to generate channels and another type of strategies. So next, please. Next slide, please. Okay, so I have to say that the funniest part of the project, of course, we enjoyed a lot in the lab, but the funniest part was the communication activities, because everyone wanted to know about the project, and this means that we did it properly. We had a lot of communication actions. So basically, the idea to communicate was that 3D printing can work for improving the fuel cells manufacturing. And for instance, in our website, we received more than 5,000 visits. Or in our Twitter account, we have more than 500 followers. And we have a couple of YouTube videos, in case you want to review the ones I presented in this talk. Okay, next slide, please. Next slide, please. Okay, and also we did a lot of dissemination activities, trying to present more the results, specific results of the project. 9 publications, one selected at the front cover and hot paper in Journal of Materials Chemistry A, a very high impact factor journal. Also, we are very, very happy that we got the Best Innovation Prize from the FCHU in 2018. That was the first time this was celebrated. But there were many, many highlights of this project all around. We count 60, but probably there were more. We attended some fairs and also conferences in which we were invited, and we even gave some keynote speeches. No? So I think that the dissemination was also very, very strong in this particular project. Next slide, please. And about the impact already achieved, let me mention that at an industrial level, there are 4 patents resulting from this project. One related to the 3D printing process, this sacrificial material I mentioned, the multi-material printing, and the new concept itself, no, for the SOFC. And also, it's very nice to see that especially the companies developing the inks and the printer, they already have in their catalog the inks developed in the project and also the printer, and they have sold many of them. So we are very happy in this sense. And also we did an LCA and techno-economical assessment of the project, and the results were very, very, very interesting in terms of the amount of material you save, the amount of money you can eventually save, and also the amount of energy you save in the fabrication. Okay, and also we tried to push for increasing the awareness about 3D printing and energy at a social level. No? Next slide, please. And finally, well, the exploitation plan was defined on the basis of this IPR protected. We also generate a specific document, the plan of use and dissemination of the foreground. Specifically, we develop business models, business plans for the different products, in 3 products that were outputs of this project. We created an industrial advisory board, including, of course, all the partners, but also Bosch or Therpotec or Print 3D Solutions, so specific companies in the field. And now to deploy and to finish with the exploitation plan in the next, we want to look for investors, and also we have some technical funding that was reached after to finish with all the things that were, of course, still pending after these 4 years of work. No? In this sense, in the technical funding, we are part of the new SOC project from the FCHU, in which we try to make large area 3D printed cells to be included in real stacks from Solid Power, Samphire, Elcogen. And also I have to highlight that we are very happy that we were awarded or labeled with the Solar Impulse as one of the 1,000 efficient solutions that could change the world. No? Probably it's too much, I don't know, but we were very happy in any case. And I think that this should be all, from my side. And thank you very much for your kind attention.
Thank you very much, Albert, for this excellent presentation. It's really exciting to see all the results you have achieved in this project, starting from scratch and really innovative. Your motto was print your energy, right? I was expecting to, at the end of the project, to be able to have a 3D printer here at the FCHU office, maybe to print our stacks. But we're not there yet. Maybe in the future.
You will have it. You will have it. Dionysius, don't worry about it.
Yeah. Thank you very much. It's really impressive to see also that you have slightly had several side effects. This fact of the corrugated electrolyte was something that you did not expect at all to develop within the project, and you were able to do it. So it's really great to see.
Yeah. Okay.
We can,
I think that in this sense already, and this is very interesting to see the potential of 3D printing. You have things that you never imagined.
Yeah,
that's the point.
Indeed. Thank you, Albert. And with this, we can move on to the next presentation, which is on QSFC, another manufacturing project. And here I would like to give the floor to Markus Rautanen to walk us through their achievements.
Thank you, Dionysius. I can't see the slides at the moment. Are they on or not? Okay, excellent. Now I can see them. So, good afternoon, everybody from Finland. It's already afternoon here. So, I'm Markus Rautanen from VTT Technical Research Center of Finland, and I'm the coordinator of this project QSOFC. So, this QSOFC project, this is addressing one of the, what I think is a sort of key issue in fuel cell manufacturing, especially with high temperature fuel cells, that is trying to take the manufacturing out of the laboratories to industrial facilities and develop methodology for mass manufacturing and quality assurance. Our project partners in this project include Sandvik and Erlinger in terms of interconnect manufacturing, Elgogen with cells and stack manufacturing, and then Hycotech and Myko, two specialist companies supporting ceramics manufacturing and interconnect quality assurance, and then two research centers, VTT and ENEA, supporting the activities. Can I have the next slide? The clicker is not working. Thanks. So the project has just finished. We started in 2017 and now finished in 2020 after 6 months of project extension. And like I mentioned, the focus of the project was to develop mass manufacturing and quality assurance for all key parts of the SOFC stack manufacturing value chain. So that mostly includes interconnects, starting from steel to coating to ready interconnects. Obviously, a lot of work developed for cell manufacturing, and then obviously stack manufacturing and quality assurance. Our sort of high-level target for the project throughout the project has been 50 megawatts per year stack production volume at a cost level of 1,000 euros per kilowatt. So all of the things that we have developed, the focus has been for this initial mass production volume and cost level. Next one, please. So some technical highlights from the project. So first of all, about interconnect manufacturing. In general, the challenge with interconnect manufacturing is that basically there are no faults allowed in the interconnects. And it's not a very simple part because often it consists of several steel parts. Some of them can have different coatings, some are plain steel, and then those parts are formed somehow and brazed or laser welded together to form the ready interconnect. So the quality control for that part needs to be very, very stringent. Next one. What we have done in the project is that we started with a full failure mode and effect analysis for the whole interconnect manufacturing process, from steel to interconnects. And there was a quite large number of steps identified that needed some tweaking or changing to make sure that any possible fault does not progress in the manufacturing of the interconnect, and to improve obviously the production yield and quality. And what Erlinger and Elgogen have also done during the project is that they have sort of introduced the concept of full backwards traceability for the interconnect. So that means that that they can now mark all the ready interconnects with a laser marking of data matrix codes that pertain the important aspects of the interconnect, its manufacturing parameters, components, batches, so on, so that if there is ever some fault in there, it can be traced backwards into production, and therefore, again, making the production better in the future. And one sort of interesting aspect is that the steel production lines at Sandvik are now also ready to accommodate mass manufacturing volumes. So they are actually able to deliver steel and coated steel materials at quite significant volumes. Next one, about cell manufacturing. So with cells, the challenge is that each cell consists of quite many layers, some of which are very thin. So even relatively small defects in the cell manufacturing process can cause quite a lot of performance, poor performance basically, or higher degradation for the cell. So what is really needed in mass manufacturing is basically 100% of inspection of every cell so that no unwanted defects can progress in the manufacturing process. Next one, please. What we have done in the project is that our project partner Higutech has developed this visual inspection system for cells together with Elcogen. So basically this system can detect and analyze the cell quality in 10 seconds. So cell goes in, it does the analysis, it can classify the defects into 6 different categories and detect defects down to about 10 microns in size. All of this in 10 seconds per cell. And this system now has been validated in Elcogen AS cell production lines. And Higutech has actually now launched this as a new product for their product inventory, offering it to fuel cell manufacturers in Europe and worldwide. So this I think is one of the very nice results of the project. And Higutech is also exploring other possible markets or applications for this technology. Next slide, please. Can I have the next slide, please? Yep. About stack management, one of the things that we are focused in process, we mean a process that takes that is basically taking place between stack assembly and shipping to a customer. So typically it can include heating and sintering steps, anode reduction, different quality assurance testing, and cooling down. And what you should notice from this slide is that all of these steps need actually fairly dedicated equipment. So test rigs with furnaces, explosive gases, electronic devices, and so on. And they take a significant amount of time. So this is actually one of the sort of key steps that affect the stack manufacturing capex as well as the capacity of the facility, because we are talking about typically of hours here, and if we are talking about significant volumes, that's a big issue. So next one, please. So during the project, what we have done is that we have tested 4 different ways of reducing the conditioning process, basically time and effort in that, by testing about 30 stacks with different process variants. And obviously, if we change the conditioning process, the quality of the stacks need to be at least as high as it is with a sort of conventional process. So we have needed to carry out fairly significant amount of statistical analysis of the results. And the sort of high-level outcome is that with the developed new conditioning process, the reduction of time is about 75% compared to the conventional conditioning procedure. And this obviously transfers itself to the capex reduction, and it also means that this is a very cost-efficient way to increase capacity, because now with this new conditioning method, the same facility can produce 4 times the amount of stacks than before the project. So very efficient way to scale up production capacity because no extra capex is needed. Next one, please. Short summary about the project. So I think we have reached quite well all of the high-level targets of the project. We developed a number of methods for mass manufacturing and quality control, hopefully putting the European fuel cell industry into a sort of good position once the volume increases start to be there. During the project, we have launched a number of new products, and as a one sort of nice aspect of the project is that based on the very good results from the QSFC and IndoSFC projects, Elcogen has also secured a 12 million euro loan from the European Investment Bank for further R&D, as well as in building a sort of first of its kind cell and stack manufacturing factory that will be located in Tallinn, Estonia. And the capacity of that factory will be about 50 megawatts per year. And the building is scheduled to start early next year. So I think this sort of shows that the project has been very useful. And I believe that we have made very good use of the funding received from FCH.JU and sort of been able to leverage that to produce further results and products and innovations, and also jobs in the new factory, for example. But I would still like to point out that I very much believe that this is just the first step in taking the fuel cells out of the laboratories to the actual manufacturing facilities. And in the future, we need much and much more of this kind of effort to really realize the benefits and the cost levels that the fuel cells should realize. Because we need to keep in mind that some of the competing technologies, like the internal combustion engines, they have been developed. The manufacturing, the quality control of those machinery has been developed for about 100 years. So we have a long way to go with fuel cells, but I very much believe we'll get there, and this type of public-private projects are a very good first step towards that. And I think that's all I had. Thanks a lot for your attention.
Thank you, Markus. It's really excellent results, and it's a very innovative project. We saw the machine vision inspection tool that you have developed there, which also won the Innovation Award a couple of years back, but also a project that is hugely impactful to an SME that's trying to scale up their manufacturing. And you have shown in a great manner how the project has helped them get the EIB loan. With this, we can move on to the next project, which is Project Low Cost IC. It's moving in a similar direction, trying to improve the interconnect manufacturing. And I can now give the floor to Henrik Lund Fransen, who will walk us through their achievements.
Yeah. Hello, everyone. Thanks for the introduction, Dionysus. My name is Henrik Lund Fransen. I'm from Technical University of Denmark. I'm trying to get the slides to work here. Could you put the slides on for me, perhaps? Okay, yeah, I think it works now. Okay, first some general information about the project. It's, as the title reveals, it's about increasing the robustness of the stacks to, again, decrease the capex, but also in the meantime, have a low-cost interconnect coming out at the very end. So the project has been running for a bit more than a year when the corona hit us. So now we're about midterm in this project. And given a intermediate idea for an extension, then we'll be ending a year and a half from now on, approximately. The budget is about 2 million euro, and in the project, as you'll see, there's 10 partners, primarily from the industry. So, hold on a second here. Next slide, yeah. So the objectives of the project then is to, again, decrease the cost of the interconnect steels. The interconnect steels, they are about a third of the total cost of an SOFC and SOEC stack as it is now. And this you would like to decrease if you want to come down in total cost for these units in the future. And especially the current steels are very expensive as they are produced a special way with very little silicon in them. So there is some potential to reduce the cost, and we have said that we want to reduce the interconnect cost by more than 80% in the project. And of course, when you replace something expensive, you better find a mitigating route for not making it worse. So therefore, there is some coding development in the project as well to make the cheaper steels do well as well. And then another target for the cost in the project is to have roll-to-roll processes being put into the manufacturing of the interconnects, again, to reduce costs of the manufacturing. And the second target of the project is to also look into increasing the lifetime. And this is especially the contact between the cell and the interconnect we are addressing here. And we have found a way to reduce reduce the loss of contact by increasing the toughness of this interface. We have promised a toughness increase by more than 200% with a special contact layer. I'll show you a bit about that. And then another way of minimizing this loss of contact is to also minimize the stresses in the interface between the cell and the interconnect. And this we are aiming towards doing by optimizing the flow distribution inside the stacks. So the consortium is built of these 7 companies. Going from the very left there, there's a steel manufacturing, a French steel manufacturing, Abraham, and they're supplying the steels. Those are to be coated at Sandvik in Sweden and shaped then after the coating at Borit, Belgium, and then Techno-Italia is the company who are to print these contact layers I was just talking about, and they have this very nice, fast drop-on-demand printing technique. Borit is using this hydroforming to shape the interconnects, and Sandvik is using a PVD coat. And finally, these new supply chain is to be tested at 2 manufacturers. So that's Sunfire and Solid Power, operating at 2 different temperatures. So Sunfire operating at a bit higher temperatures, say 850, and Solid Power around 750. So we'll test the inventions at different temperatures. To support all this, we have Chalmers to look into the steels, Jülich on the shaping and the stack design. We are looking very much on the contact layers, and then the ABL will do a cost analysis of all these things. So in the next couple of slides, I'll show you a few highlights from the project. So here there is a schematics showing how this hydroforming is done. So there is a high pressure built on one side of a flat metal sheet, which then shapes the sheet. And as you can see from the picture just down below, it comes out very nice after such a treatment. However, when we then do the shaping, and we did the coating first, then you'll see that the coating is actually rather cracked up at the convex surfaces of this shaping here. And the graph here shows the amount of chromium evaporated during the first couple of hours of the lifetime of this interconnect piece. So you'll see in the very beginning there is a higher chromium evaporation because the coating is broken. But as the time passes by, let's say within 50 hours, you have a steadying of this chromium evaporation, meaning that now we are back to the normal non-broken state, as you can see in the micrograph to the right-hand side. It's a solid interface there. And then the other highlight I'm talking about is these new low-cost steels. How are they performing against the high-cost steels? So the new cheaper ones are the orange dots there in the left-hand side graph, and the more expensive ones are the gray, as you will recognize, maybe Cooper from this you see the amount of mass gain, meaning an indicator for how much corrosion there is going on, is about the same for the two. So at least in terms of performance in the lab, it seems like they're performing very much the same using these very nice coatings. However, when we take them to the stack, and this is results from a Sunfire stack, we have observed some degradation, which is a bit higher in the stacks, and we're not quite certain what this is. We're looking into that right now. And you could say, if we are to point to any risks in the project, is that this coating is not going to survive a high temperature. But it could be due to this cracking, which is not properly healed before we start initiating the stack. So we're looking into this. The third highlight here is on a new reactive bonding principle. So when you have typically the interconnects to be bonded to the cells, it's done through a contact layer, which is typically ceramic from the very beginning. So when you put it inside the stack and you are heating it up, well, it actually wants higher temperatures than you are allowed to give it due to the corrosion of the interconnect and so on. So there's not a proper sintering of this contact layer. So the concept here is to throw in steel, or not steel, but metallic particles. For instance, now illustrated here, copper and manganese metallic particles. And once they see the air temperature and high temperature, well, then they start oxidizing, and putting them in the right ratio. Well, then you'll end up with a conductive spinel. And this oxidation inside is giving some nice reactions, both to densify this contact layer, but also to give good adhesion to the ambient surfaces. And when we measure the, and when we measure the toughness, here you see fracture toughness for the different materials. So there's copper, manganese, and green, and the yellow ones there, cobalt, manganese. Then you see, as comparing it to the reference to the very right in gray, well, then you see the fracture toughness is increased dramatically. So there is measured after assembly, after some aging at two different temperatures here, and you see the copper manganese is tremendously much tougher than the existing contact layers. Then another highlight is we have developed a new multi-scale multiphysics model, and this is all built within a established environment, so it comes from multiphysics. But the main idea is that we're using something called homogenization, which allows us to run everything much faster. So, for instance, here you see a 30-cell stack that has been simulated with all the physics we want. So now it's just a few of them plotted here, and also mechanical stresses and so on. It's a Sunfire stack, and the main point is that we can now simulate everything about 100 times faster than what we could previously. And this makes it possible for us to, say, change the signs of, say, interconnect to see if there's any gains in the stress field. And to also really understand the stress field, this model is not just multiphysics, it's also multi-scale. So we are able to look at local stresses where we may expect loss of contacts. Okay, so to conclude, well, one of the main targets here was to demonstrate this roll-to-roll principle, and by showing that the already pre-shaped interconnects or pre-coded interconnects be shaped, well, then it says it's possible to do the coding before we shape, which is very important for this roll-to-roll process. We have also showed that the low-cost yields can perform similar as the high-cost yields, at least in lab. And we do need to look further into what's going on in stacks and understand why they're not performing exactly the same there. Maybe there's a way around it. And then finally, there's these high robustness contact layers presented, and the principle of this reactive bonding. And then I also showed some results from our multi-scale multi-physics model to develop the flow fields inside the stacks. This is currently ongoing. Yeah, so with this, I'd like to acknowledge the funding, of course, and thank you for the attention. And then also thanks to Dionysus for giving some nice support there. Okay.
Thank you, Henrik. Thank you very much for the presentation. Another very promising project can have a great impact, not only on the two manufacturers that are involved directly, but to the fuel cell community as a whole. And we're looking forward to see the results that come out in the second half. We can move on to the next and final project, and this is a PEM project this time, Project Grasshopper, where we will have Marianne Wittmar presenting its highlights. Marianne, the floor is yours.
Good morning to everybody. I hope that technology will work now. I will show you a few slides about the Grasshopper project, which was, let's say, 3 years project that was extended for another 6 months. Yeah, it works. So what are the main objectives for this project? It was, or it is still, development and demonstration of next generation modular megawatt size power plant, fuel cell power plant unit, with a lot of improvements in the number of fuel cell technologies like MEAs, stacks, and system. Of course, with the need for the substantial cost reduction for all subsystems, high stack power density and efficiency, a long lifetime expectation, and a lot of simulations done for the system efficiency and availability. The second is how to improve also the stack manufacturing process in all phases to, at the end, to integrate the system into the flexible demand-driven operation on the current ongoing smart grid systems. To demonstrate 100 kilowatt submodule unit with a long validation period, and of course some dissemination activities. The first part was, or is, running the flow field modeling, so how to design and check the fuel cell stacks components. It was done a number of CFD simulation to prove that design of the stack components are okay, and to find possible improvements inside the building of the fuel cell stacks. Simulation confirms a very good distribution of media in the cell. And it was done also a number of checks how the fuel cell will act if some, let's say, events are happening inside. So you can see that with the GTL-enabled compensating, the results are quite good. So the simulation proves that the design is okay. The next important part was the construction or to the production of the MEA. And within that, the results are quite good, exceptional results actually. So the reduction of the platinum was quite high, so 81% for the grasshopper stacks. So the grasshopper stacks or MEAs are let's say codenamed GH1, 2, and 3, and you can see that the thickness is different and the reduction of the platinum is really high. The next important thing is that at the same time, not only the cost improvements, also, let's say, the durability of the MEA is quite high. Currently, the tests are running for 5,500 hours, and no degradation is observed during this time on that MEA currently under test. Within the work package number 4, the improved stack design and production is executing. So the stack design has been completed. There are actually 2 designs. One is for the 200 square centimeter stack size and the other for 300. Both are targeting the performance of 0.68 watts at 1 amp per square centimeter, and the size should then at the end show the 100 kilowatt system that will be tested and installed in the net stack surrounding in the Netherlands. So the pilot plant will be located in Chemical Park in the Netherlands. The permit is in progress from the province, and all, let's say, necessary documents are already prepared for the project. Inside the work package 5, which is about system modeling and performance optimization, a number of models has been prepared and tested. The aim for this, or the results from this modeling, would be used for the final tuning of the system. Well, the most important thing is that although this is a stationary application or a system, it will be used for the dynamic implementation, where our plant will be used for the smart grid connection, where you can do a lot of different changes with the power due to the compensating of the grid or some other purposes. The Grasshopper pilot plant was produced in Seville, in Spain. You can see here a number of pictures how the system is built. It is the base of the system is a large container that has all the BOP and fuel cell parts inside. It's designed that it's easy to maintain, so it's a skid-based that could be, let's say, inserted and also split it between the BOP and the fuel cell and the the power electronics. The current status is that system is under the factory acceptance test. So the BOP circuit is testing, control loop are adjusted, and for the KPIs, the basic elements are now in place. So automation and software programming is also done. Still in progress, of course. Inside the work package 7, it is how to interconnect the fuel cell power plant to the smart grids. So you can see that smart grids has some phases how the system could be used. So starting up, running, shutting down. And here you can see the dynamics of the power plant is very important. The system could be used then inside the smart grids for the energy trading, for the demand side management. So when the electricity is needed, it could jump into the operation. How it's done, the smart grid part is a kind of coprocessor inside the control system. So the requests are coming from the smart grid center, transferred to the appropriate part inside the power plant, fuel cell power plant, and then reacting and acting as needed. Of course, at the end, the KPI will be calculated. Of course, it is very important that the power plant is scalable, so it could be, let's say, scalable to several megawatts, with adding several fuel cells or several systems into the one unit that is controlled by the demand-side management software. For the dissemination, yes, you can see, let's say, the current status in the work on the web pages, which is here presented, and of course some videos were done with the overall operation for the plant and how it was produced, transported, and so on. At the end, who are the project partners? 7 partners altogether, universities and 2, let's say, companies, and yeah, here are the names of all the companies that are working on the project. Thank you very much.
Thank you, Marian, for the great presentation on Grasshopper. It's good to see some results as well from PEM projects, which seem to be underrepresented in this panel. And with this, we have finalized with all the presentations from the project, and now we can move into the Q&A session, which you can see we have had a very active audience, and we have quite a lot of questions. I will start with the same order as we did with the presentations, and as questions keep coming in, I might have to come back to you again. So starting with you, Albert, I have a question regarding the corrugated cells. Everybody seems to be very interested in that, and there's no surprise. It's really, really impressive. Do you have already some interest from OEMs that are willing to explore this further with you and see how they can integrate it into their processes? And do you already have any insights on what sort of strains you might have, strain concentrations in the corrugated cells?
Mm-hmm. We didn't calculate this yet, but the nice point, I think, with this development, with this specific development of the project, is that now we have the opportunity to continue developing it in the new SOC project, no, that is focused on the next generation of solid oxide cells, no. So yeah, there we work in close collaboration with Solid Power, Sunfire, and Elcogen that are also involved in the project, and we are developing together the best design to incorporate this specific advantage or similar advantages in their stacks, no, in the cells that couple well with or fits well with their stacks, no. And I think that this is the good point with 3D printing, that you can adapt the design to their requirements, and then you can look for specific advantages for a specific the designs of stacks, no? So it's not like a solution you have to work around to develop the whole product, but probably it's more in the other direction, no? So you already have a product and you want to try this solution for improving, in this case, for instance, the power, the total power, no? Because you increase the active area per projected area, and then you can include it and you can test it, no? I think that this is the real power of this technology, no?
Indeed. And I remember in the midterm review of the project, we were discussing if you see the potential by the end of the project to have, these machines in parallel replacing production plants in the future. But we see also the potential of what you say, that you don't have to do that. You just have to also focus on what are the advantages you can provide to already existing processes.
Exactly. No, for me, the good point of this kind of tabletop pilot plant, as somebody can call it, is that you have all the process in the same place, so no need to move things, and also you can keep a very clean atmosphere, a very clean environment, and that's very, very important in ceramics, no, at the end of the day, because of course the defects are one of the points to work about and to look into detail, no, as Marcus, for instance, presented, no.
Mm-hmm. Okay, and people are curious to know about the speed of the process and the sizes that you can actually print. Could you tell us a bit more about that? Talking about the speeds, how much time would it take for a full stack, for example?
Yeah. Well, the idea is, first of all, the printer we have, I said 20 by 20, but it's 30 by 30 indeed, 30 by 30 by 30 centimeters, and 10 in height, no, but still the company have a new model that is 60 by 60. So you can imagine printing at a time up to 4 stacks of 5 kilowatts. Okay, in this volume, more or less. And about the speed, it takes around 24 hours to do the whole deposit of the stack. Okay, then I have to say here that our initial idea was to try to print it, no, but we found some problems during the project, and we are not able to print the whole stack at this moment, no. But according to the speed we can fabricate and all the intermediate steps and so on and so forth. These 24 hours would be the time for the whole platform to be printed. So 4 stacks in 24 hours, no.
And with respect to the capacity of the stack that would come out of the printer?
Yeah, it should be 5 kilowatts according to our expectations.
And if you do manage to get it with a corrugated cell, that would be 60% above, I guess?
Exactly, exactly, that's true.
Okay, great. And so with respect to the supply chain, it should also be impactful in that sense, this project. So do you think that companies could specialize in the provision of ink, 3D printing robots, or do you think it will come all from one supplier?
No, it should not be like that. So we did it, of course, with the few companies that are currently that has the capacity of doing it, but it can be extended to other companies. In fact, of course, there is a replica of this French machine. In this case, it's 3D Ceram, the company that is developing the machine. There is a replica in China, for instance, right now. No, a Chinese company was able to replicate and is also developing the same. Also, there are other options in other. There are not many companies developing 3D printers for ceramics, but there are a few, no? And some of them are doing very well. So it's not just one company. And about the feedstock, then, well, sometimes it probably it's better if it's coupled to the 3D printer machine because it goes together, but in any case can be fabricated by any company that is able to produce powders or slurries in general. So it's nothing very difficult.
And talking about what you mentioned about China and all the intellectual property rights that you have developed here, you mentioned that you have 4 patents developed in the project. Could you tell us a bit more about how you wish to exploit this product further? Who will own it? Who will move forward as the supplier?
So three of them are specifically on the printer developer. So they have the right for the exploitation. Because, well, some of them are very specific to the machine, very related to the machine, and another one that is a sacrificial material. It's an idea that came from them. There is one on our site, on IREX site, on our institute, and it's more on the SOFC concept. And for the 3 first, they are exploiting them because they sell the machines and they have already a market on this. And for the last one, we are looking for the investor, in fact, to start the exploitation of these new concepts.
Okay, great. Good to hear that. Thank you very much, Albert. I think we will move on to the next presentation, and might have to come back to you with more. So, Marcus, moving on to you. We heard a lot about the new manufacturing plant being prepared right now from Elcogen. Could you tell us, you mentioned that this project has contributed to that development. Do you see the stack conditioning processes that are developed within QSOFC being directly adopted by the manufacturing plant in Estonia? Will the machine vision inspection tool is it going to be used there as well? Could you tell us a bit more about that?
Well, the best conditioning procedure that has been developed in the QSOFC project that has been adapted already by Elcogen in their current production. So I'm sure that will be also adapted in the factory, unless they or us come up with something better before the factory is ready. About the second question, your second question was about the vision inspection system. That actually, I don't know. I don't know if they will implement it there. I would assume yes, but I don't know that personally. So I suppose it depends also on the volume. What is the initial volume? Because obviously the factory will start at 0 volume when it's built up and then ramp up to full capacity over some time. But how many of these will be there, I don't know.
Okay, thank you. And with respect to what you mentioned about the stack conditioning process, there's always a trade-off between how much time and energy you will spend on the stack conditioning and your confidence with respect to the performance of the stack. Do you think there is more potential in reducing the time and energy and keeping the confidence in the stack?
Well, I'm sure there's always more potential in doing that. I mean, the challenge comes mainly from the aspect of testing, because as we have done during the project, the production yields have increased, and when we start to go higher and higher in production yield and in quality, you need to test more and more. So it's not enough to test maybe some tens of stacks, but you would need to have to start testing hundreds of stacks, and that takes time to validate any better conditioning procedure. So I'm sure that we'll be able to make it better over the next years, but the better it gets, the more time it takes to improve it, actually.
Indeed. And with respect to you mentioned that there is a significant impact with respect to the reduction of the capex by reducing the stack conditioning time. Could you quantify this for us with what you have achieved within QSOFC?
Yeah, Elcogen has quantified it. If I remember correctly, that's about 20% of capex reduction of stack cost.
Okay, thank you. Thank you. And within your project, your one of the objectives that you had was to develop and validate quality assurance methods that were independent to the stack manufacturer and the stack processes. Could you tell us a bit more about how you will impact the fuel cell community as a whole? I see that you have 7 publications already made through QSFC. Could you tell us a bit more about how people can access more public information on your project?
Well, I suppose our sort of starting point for this project was that we will have parallel tracks. So we will have sort of independent track for interconnects and cells and stacks. So, for example, taking Elcogen, they currently manufacture and sell their cells to several clients, not just the Elcogen stack production, but other clients as well. So all of the benefits that we have developed here that have gone to, for example, cell production are sort of available for all of their clients in Europe and internationally, of course. And same goes with, for example, steel production. So starting from Sandvik's steel and coated steel production to Erlingklinger's interconnect production, those are also the methods are available, the products are available for all the other manufacturers also to purchase. So like Sandvik, they produce steel for many clients, and Erlingklinger interconnects for other manufacturers as well.
Okay, thank you. And I remember in your closing statements, you were very positive about the outcomes of the project, but you mentioned that there's still a lot that needs to be done, correct? And we have a very vibrant European supply chain. It seems as it evidenced by these 2 projects. But it would be nice to hear from you. What is your insight on what needs to be done in the following steps?
Well, I think it's going to be a little bit. Yeah, I think it's just going to be a little bit boring answer, but
no answer. No answer on the funding, on requesting funding. Must be something else.
Well, I suppose we just need to keep doing what we are doing at the moment, but more and more of that. That's what I sort of meant with like internal combustion engine. If you think about it, these guys have developed the manufacturing and quality control of that for 100 years, with annual budgets of billions going into the manufacturing and quality, billions in Europe. So we have a lot of they have a lot of head start in that industry. So we just need to make sure that we can take small steps as a fuel cell community with these kind of projects, with self-funded projects from the manufacturers and joint initiatives to make that happen, that we can really move out of the laboratories to the factories.
Okay, thank you very much, Marcus.
Thank you.
Now on to you, Henrik. We have a couple of questions from the audience on low-cost IC. One of the questions is that in order to reduce the costs, one of the major implications is the thickness of the interconnects. And could you tell us a bit more about what kind of thickness ranges you're focusing within low-cost IC? You are mute still right now. We cannot hear you. You're still on mute.
Thanks. Okay, I'll repeat that. So we're trying out 2 thicknesses and 0.3 millimeters and then 0.5 millimeters. And obviously we get better shapings when we use 0.3 millimeters. We could exactly get the shapes we wanted. And then 0.5 millimeters, that was a bit more tricky to get the desired shaping with the hydroforming method. But I think that depends very much on the design of the individual manufacturer, what can be reached. But this is the range where we're working with.
Okay, thank you. And it is very important to state that in your consortium you already have 2 stack manufacturers, and there are certainly many advantages in having them. Is there a balance between the freedom that you have as a researcher and the restrictions that you get from the industry. How did you balance that in your project? Could you tell us a bit if you were?
I think they're behaving nicely. They're very interested in what's the outcome of the project here. I think, and I think they're playing very well along. I don't think they are. Of course, they are giving some opinions about what they think is needed to meet their end, and of course that's also what we're interested in solving, right? So it's also interesting for us to hear what they have to say in that sense. So I don't think that there is a constriction between doing academic work and working together with the industry. I think it goes very well in hand.
Yeah, and it's one of the beauties of the public and private partnership that we have results that are immediately exploitable to the interested industries.
Yeah, exactly. Yeah.
Thank you. Marian, I would like to ask some questions to you as well from the audience. We have one question regarding the hydrogen input into the pilot plant in the demonstration. Could you tell us a bit more about where this hydrogen will be sourced from?
Yes, in Netherlands, it is chemical park. It's a factory that has a lot of spare hydrogen. So this hydrogen will be used for this unit. So it's actually the hydrogen that is otherwise, let's say, available for this pumping station, and the second part will be used for the system.
Okay, thank you. And do you see a lot of replication potential in demonstrations in Europe and overseas in this scale? Which are the main markets that you foresee will be unlocked in the near future?
Well, let's say in the near future, maybe not, but in the, let's say, a little long-term situation, I could see a lot of, let's say, implementations. Because currently, of course, the hydrogen is the main point, let's say, the cost of the hydrogen. But due to the fact that the electricity is currently rather very, very cheap in the market. So in case that this will not be any more situation, of course the hydrogen will be important. And of course the hydrogen has potential due to the, let's say, possibility to be stored and used when needed.
Mm-hmm. And I saw that you are also focusing on improving the power density while maintaining the durability of the system. This will be a central, let's say, it could lead to the tapping of new markets in the heavy duty transport sector as well. Do you see this as a potential, and do you see the possibility of achieving these power density requirements of the heavy-duty transport sector?
Yes, definitely. I suppose that this is one of the really good results from the project, that for the rather high density, the durability is really exceptional so far. Of course, 5,500 is still not 20,000, but the degradation itself is really minimal or almost not existing at the moment.
Great. Good to hear these results. I think we have reached the end of the time now. I would like to thank you all for your excellent presentations and excellent interactions. And also a big thank you to the audience for being such active participants and sending in us their questions. And with this, I think we can close the session. Thank you very much to all the presenters.
Thank you very much, Dionysius. Thank you.
Thank you for your support.
Thanks a lot.
Bye, everyone.
Bye-bye.
The people I've met in Tokyo, Fukushima, and Nagoya told me about the vast potential of hydrogen in Japan. With such hopes for hydrogen, I wondered if it could help achieve the dream of sustainable mobility. Innovative people everywhere are driving the ambition of a clean, carbon-free future. I traveled to the Netherlands, in Delft near Rotterdam, to meet a group of passionate young students who've pioneered the hydrogen revolution in mobility. I had a moment to chat with the Forza team, a group of students who spent one full academic year working tirelessly on a pink, carbon-free hydrogen fuel cell race car. I talked to a few of them.
Alright, sounds good. Our primary goal, it goes back to our mission, which is to promote clean hydrogen technology in the transport sector. If you tone that down to kind of really why we're here, it's to race a car very fast around the track on hydrogen power.
And we race against petrol-powered cars, just normal cars, in order to show the potential that hydrogen has and the future that hydrogen has in front of it.
So who are they? Why do these students do what they do?
I just finished my bachelor's degree, but I think there are very few groups in the world that allow people of my age and experience to do what we're doing, to make a hydrogen race car within 1 year and to make it go around the track as fast as we do. It's really quite exciting stuff, and it's quite an honor to be able to be a part of this team. So that's a huge motivation.
We are a really motivated team. We are fascinated by technology. We all study it at the university here, and that makes it really, really exciting to work in this environment, because motivation of others motivates you, and getting the chance to work on a real project, full scale, is just a unique experience that just gets everyone super happy about it. Although there are ups and downs, of course. It's a hard and long year, but every one of us is making the best of it.
The question that kept coming back to me was, why hydrogen? Why use fuel cells in such a competitive field?
Hydrogen is something that's emerged in the past few years, and it's something that has a lot of potential.
Fuel cell technology can basically be applied to any kind of mobility. Like a race car really pushes the technology to its limits. If a fuel cell can work in a race car, it can work anywhere.
Fuel cell technology can have a wide range of applications, and I just really believe they can be widely used in the future for many, many types of applications.
The way they talked about fuel cells gave me the impression that there was some sort of higher purpose. I asked them if they felt like they were changing the world.
We're definitely putting some work into that. I mean, in the end, what we're contributing to is a much bigger vision, the electrification and the moving towards sustainable energies and sustainable technologies for the future. So in that sense, we are for sure contributing to such a vision for the future.
I think it is important that we do find an alternative to fossil fuels, and hydrogen, as I mentioned, it's becoming quite a possibility, but the only thing you can do is try. You have to try your best, or else all is lost.
I was blown away by the drive and ambition of these students, the mindset of a new generation, the way they decided to take on the Goliath of climate change with their own hands. But race cars, or cars for that matter, aren't the only thing that need an update. In the US, a massive shift is on the way. In a country where retail and e-commerce are two huge pillars of the economy, change can be seen at different levels too. In warehouses where millions of items are stored, some companies have started using hydrogen fuel cell forklifts instead of gas or battery-powered alternatives. And hydrogen-fueled vans and trucks are already on the road, delivering your parcels to your door. In a way, fuel cells are powering a small revolution in logistics. The next step of my journey leads me to the United Kingdom. In Oxford, I met with Joe Bamford, an entrepreneur who put forward a vision powered by hydrogen technologies. His company is making thousands of buses across the UK to further the zero-emission ambition.
What's driving me on this is to think about the world and how do you get mass adoption of zero emissions. And for me, you get mass adoption of zero emissions when it costs the same, when it does the same, and when it's as easy to fill up It shouldn't be anything special in reality. It should be just something we do as a matter of course. We think buses are a great place to start with hydrogen. There are 40,000 buses in the UK. Battery buses will do 60% of the distance of a diesel bus, so I would imagine 30% of the UK market will go hydrogen within the next 5 years.
Joe Bamford kept telling me about the real goal. Make it as easy as possible for the user.
When it comes to zero emission, there are two zero emission solutions, batteries and hydrogen. Why do I believe that hydrogen works better? Because it does everything that we have today. Hydrogen, we can make it at a wind farm, turn water into hydrogen, stick it on a truck, deliver it to a filling station, fill a car up in 5 minutes and off we go. It just works in quite the same manner, and I think it has to be very practical, these mass adoptions. Don't try and change too much, and human behavior is the most difficult thing to change.
Going even further, I found out about another use of fuel cells that is pushing this new reality into the realm of dreams. Beyond public transport or freight, innovation has changed the lives of a small crew.
Alors Energy Observer, c'est un véritable smart grid flottant qui représente un cercle vertueux de l'énergie, associant la production d'énergie renouvelable avec la consommation de ces énergies. On stocke quotidiennement nos énergies à travers nos batteries, mais on n'en a pas beaucoup pour être léger, et l'hydrogène sur le long terme. L'hydrogène, c'est vraiment notre prolongateur d'autonomie, c'est le couteau suisse de ces énergies renouvelables que l'on produit quotidiennement.
This is Victorien Erussard, the skipper of the Energy Observer, a vessel that launched in Saint-Malo, France in April 2017. It is the first in the world to both generate and be powered by hydrogen. Its expedition around the world provides durable solutions for energy transition.
On a joué un véritable rôle d'ambassadeur avec les médias, les industriels, les politiques et les citoyens. L'idée, c'est d'essayer d'équilibrer nos consommations énergétiques. Lorsqu'on n'a pas assez de vent, lorsqu'il fait nuit, lorsqu'il n'y a pas de soleil, on démarre notre pile à combustible qui nous permet d'aller partout autour du monde.
The crew chose hydrogen for its characteristics.
Pour moi, l'hydrogène est une solution d'avenir dans le sens où on peut stocker un maximum d'énergie dans un faible volume. Avec la mobilité des industriels sur cette production d'hydrogène et ce stockage et les différentes applications qui sont développées, je pense qu'on est sur la bonne voie.
In Wales, I spotted a unique, fierce-looking car. I met with its designer, Hugo Spowers. Hugo is a motorsport engineer who had a business designing and developing racing cars. But something always felt wrong.
And I got out of motor racing for environmental reasons, thinking that the only future for sustainable transport. Then I heard about fuel cells. And I realised that therein lay an opportunity for me because the technology existed, but we needed to build cars differently.
Hugo and his wife Fiona are the founders of the car company River Simple.
So it's not surprising that fuel cell vehicles are taking longer to come to market because it is so different to a combustion engine that it is much easier to design a car from a clean slate around the characteristics of hydrogen technology than it is to try and shoehorn the hydrogen technology into the sort of cars that we've optimized for the last 100 years around combustion engines.
I asked him the same question I asked the team at Forza. Why hydrogen?
I don't believe that there's anything that can be remotely as efficient as a hydrogen car for the sort of range to which we've become accustomed. So that's why we're developing hydrogen cars. And it wasn't until I came across fuel cell technology that I saw a sustainable powertrain on the horizon.
Hugo and his wife Fiona are dedicated to the idea of sustainable mobility.
Our purpose statement is to pursue systematically the elimination of environmental impact of personal transport. I'm very optimistic about the future of mobility. We think we're so far from a sustainable system at the moment. We need a quantum shift. I think we're going to see huge changes ahead of us. But those changes are now, I think, unstoppable.
Unstoppable. When mobility is responsible for such a large part of global carbon emissions, those changes can come fast enough. From a dedicated group of students in the Netherlands to industry experts in the UK, from buses to race cars and forklifts, initiatives everywhere are popping up as proof that transport can reinvent itself towards a new, cleaner mobility model. I really wonder if hydrogen could decarbonize other sectors too. People I've met in Tokyo, Fukushima and Nagoya told me about the vast potential of hydrogen in Japan. With such hopes for hydrogen, I wondered if it could help achieve the dream of sustainable mobility. Innovative people everywhere are driving the ambition of a clean, carbon-free future. I traveled to the Netherlands, in Delft near Rotterdam, to meet a group of passionate young students who've pioneered the hydrogen revolution in mobility. I had a moment to chat with the Forza team, a group of students who spent one full academic year working tirelessly on a pink, carbon-free hydrogen fuel cell race car. I talked to a few of them.
Alright, sounds good. Our primary goal, it goes back to our mission, which is to promote clean hydrogen technology in the transport sector. If you tone that down to kind of really why we're here, it's to race a car very fast around the track on hydrogen power.
And we race against petrol-powered cars, just normal cars, in order to show the potential that hydrogen has and the future that hydrogen has in front of it.
So who are they? Why do these students do what they do?
I just finished my bachelor's degree, but I think there are very few groups in the world that allow people of my age and experience to do what we're doing, to make a hydrogen race car within 1 year and to make it go around a track as fast as we do. It's really quite exciting stuff, and it's quite an honor to be able to be a part of this team. So that's a huge motivation.
We are a really motivated team. We are fascinated by technology. We all study it at the university here, and that makes it really, really exciting to work in this environment, because motivation of others motivates you, and getting the chance to work on a real project, full scale, is just a unique experience that just gets everyone super happy about it. Although there are ups and downs, of course. It's a hard and long year, but every one of us is making the best of it.
The question that kept coming back to me was, why hydrogen? Why use fuel cells in such a competitive field?
Hydrogen is something that's emerged in the past few years, and it's something that has a lot of potential.
Fuel cell technology can basically be applied to any kind of mobility. Like a race car really pushes the technology to its limits. If a fuel cell can work in a race car, it can work anywhere.
Fuel cell technology can have a wide range of applications, and I just really believe they can be widely used in the future for many, many types of applications.
The way they talked about fuel cells gave me the impression that there was some sort of higher purpose. I asked them if they felt like they were changing the world.
We're definitely putting some work into that. I mean, in the end, what we're contributing to is a much bigger vision, the electrification and the moving towards sustainable energies and sustainable technologies for the future. So in that sense, we are for sure contributing to such a vision for the future.
I think it is important that we do find an alternative to fossil fuels, and hydrogen, as I mentioned, it's becoming quite a possibility, but the only thing you can do is try. You have to try your best, or else all is lost.
I was blown away by the drive and ambition of these students, the mindset of a new generation, the way they decided to take on the Goliath of climate change with their own hands. But race cars, or cars for that matter, aren't the only thing that need an update. In the US, a massive shift is on the way. In a country where retail and e-commerce are two huge pillars of the economy, change can be seen at different levels too. In warehouses where millions of items are stored, some companies have started using hydrogen fuel cell forklifts instead of gas or battery-powered alternatives. and hydrogen-fueled vans and trucks are already on the road, delivering your parcels to your door. In a way, fuel cells are powering a small revolution in logistics. The next step of my journey leads me to the United Kingdom. In Oxford, I met with Joe Bamford, an entrepreneur who put forward a vision powered by hydrogen technologies. His company is making thousands of buses across the UK to further the zero-emission ambition.
What's driving me on this is to think about the world and how do you get mass adoption of zero emissions. And for me, you get mass adoption of zero emissions when it costs the same, when it does the same, and when it's as easy to fill up. It shouldn't be anything special in reality. It should be just something we do as a matter of course. We think buses are a great place to start with hydrogen. There are 40,000 buses in the UK. Battery buses will do 60% of the distance of a diesel bus, so I would imagine 30% of the UK market will go hydrogen within the next 5 years.
Joe Bamford kept telling me about the real goal. Make it as easy as possible for the user.
When it comes to zero emission, there are two zero emission solutions, batteries and hydrogen. Why do I believe that hydrogen works better? Because it does everything that we have today. Hydrogen, we can make it at a wind farm, turn water into hydrogen, stick it on a truck, deliver it to a filling station, fill a car up in 5 minutes and off we go. It just works in quite the same manner, and I think it has to be very practical, these mass adoptions. Don't try and change too much, and human behavior is the most difficult thing to change.
Going even further, I found out about another use of fuel cells that is pushing this new reality into the realm of dreams. Beyond public transport or freight, innovation has changed the lives of a small crew.
Alors Energy Observer, c'est un véritable smart grid flottant qui représente un cercle vertueux de l'énergie, associant la production d'énergie renouvelable avec la consommation de ces énergies. On stocke quotidiennement nos énergies à travers nos batteries, mais on n'en a pas beaucoup pour être léger, et l'hydrogène sur le long terme. L'hydrogène, c'est vraiment notre prolongateur d'autonomie, c'est le couteau suisse de ces énergies renouvelables que l'on produit quotidiennement.
This is Victorien Erussard, the skipper of the Energy Observer, a vessel that launched in Saint-Malo, France in April 2017. It is the first in the world to both generate and be powered by hydrogen. Its expedition around the world provides durable solutions for energy transition.
On a joué un véritable rôle d'ambassadeur avec les médias, les industriels, les politiques et les citoyens. L'idée, c'est d'essayer d'équilibrer nos consommations énergétiques. Lorsqu'on n'a pas assez de vent, lorsqu'il fait nuit, lorsqu'il n'y a pas de soleil, on démarre notre pile à combustible qui nous permet d'aller partout autour du monde.
The crew chose hydrogen for its characteristics.
Pour moi, l'hydrogène est une solution d'avenir dans le sens où on peut stocker un maximum d'énergie dans un faible volume. Avec la mobilité des industriels sur cette production d'hydrogène et ce stockage et les différentes applications qui sont développées, je pense qu'on est sur la bonne voie.
In Wales, I spotted a unique, fierce-looking car. I met with its designer, Hugo Spowers. Hugo is a motorsport engineer who had a business designing and developing racing cars. But something always felt wrong.
And I got out of motor racing for environmental reasons, thinking that the only future for sustainable transport. Then I heard about fuel cells. And I realised that therein lay an opportunity for me because the technology existed, but we needed to build cars differently.
Hugo and his wife Fiona are the founders of the car company River Simple.
So it's not surprising that fuel cell vehicles are taking longer to come to market because it is so different to a combustion engine that it is much easier to design a car from a clean slate around the characteristics of hydrogen technology than it is to try and shoehorn the hydrogen technology into the sort of cars that we've optimized for the last 100 years around combustion engines.
I asked him the same question I asked the team at Forza. Why hydrogen?
I don't believe that there's anything that can be remotely as efficient as a hydrogen car for the sort of range to which we've become accustomed. So that's why we're developing hydrogen cars. And it wasn't until I came across fuel cell technology that I saw a sustainable powertrain on the horizon.
Hugo and his wife Fiona are dedicated to the idea of sustainable mobility.
Our purpose statement is to pursue systematically the elimination of environmental impact of personal transport. I'm very optimistic about the future of mobility. We think we're so far from a sustainable system at the moment. We need a quantum shift. I think we're going to see huge changes ahead of us, but those changes are now, I think, unstoppable.
Unstoppable. When mobility is responsible for such a large part of global carbon emissions, those changes can come fast enough. From a dedicated group of students in the Netherlands to industry experts in the UK, from buses to race cars and forklifts, initiatives everywhere are popping up as proof that transport can reinvent itself towards a new, cleaner mobility model. I really wonder if hydrogen could decarbonize other sectors too. People I've met in Tokyo, Fukushima and Nagoya told me about the vast potential of hydrogen in Japan. With such hopes for hydrogen, I wondered if it could help achieve the dream of sustainable mobility. Innovative people everywhere are driving the ambition of a clean, carbon-free future. I traveled to the Netherlands, in Delft near Rotterdam, to meet a group of passionate young students who've pioneered the hydrogen revolution in mobility. I had a moment to chat with the Forza team, a group of students who spent one full academic year working tirelessly on a pink, carbon-free hydrogen fuel cell race car. I talked to a few of them.
Alright, sounds good. Our primary goal, it goes back to our mission, which is to promote clean hydrogen technology in the transport sector. If you tone that down to kind of really why we're here, it's to race a car very fast around the track on hydrogen power.
And we race against petrol-powered cars, just normal cars, in order to show the potential that hydrogen has and the future that hydrogen has in front of it.
So who are they? Why do these students do what they do?
I just finished my bachelor's degree, but I think there are very few groups in the world that allow people of my age and experience to do what we're doing, to make a hydrogen race car within 1 year and to make it go around the track as fast as we do. It's really quite exciting stuff, and it's quite an honor to be able to be a part of this team. So that's a huge motivation.
We are a really motivated team. We are fascinated by technology. We all study it at the university here, and that makes it really, really exciting to work in this environment, because motivation of others motivates you, and getting the chance to work on a real project, full scale, is just a unique experience that just gets everyone super happy about it. Although there are ups and downs, of course. It's a hard and long year, but every one of us is making the best of it.
The question that kept coming back to me was, why hydrogen? Why use fuel cells in such a competitive field?
Hydrogen is something that's emerged in the past few years, and it's something that has a lot of potential.
Fuel cell technology can basically be applied to any kind of mobility. Like a race car really pushes the technology to its limits. If a fuel cell can work in a race car, it can work anywhere.
Fuel cell technology can have a wide range of applications, and I just really believe they can be widely used in the future for many, many types of applications.
The way they talked about fuel cells gave me the impression that there was some sort of higher purpose. I asked them if they felt like they were changing the world.
We're definitely putting some work into that. I mean, in the end, what we're contributing to is a much bigger vision, the electrification and the moving towards sustainable energies and sustainable technologies. for the future. So in that sense, we are for sure contributing to such a vision for the future.
I think it is important that we do find an alternative to fossil fuels, and hydrogen, as I mentioned, it's becoming quite a possibility, but the only thing you can do is try. You have to try your best or else all is lost.
I was blown away by the drive and ambition of these students, the mindset of a new generation, the way they decided to take on the Goliath of climate change with their own hands. But race cars, or cars for that matter, aren't the only thing that need an update. In the US, a massive shift is on the way. In a country where retail and e-commerce are two huge pillars of the economy, change can be seen at different levels too. In warehouses where millions of items are stored, some companies have started using hydrogen fuel cell forklifts instead of gas or battery-powered alternatives. And hydrogen-fueled vans and trucks are already on the road, delivering your parcels to your door. In a way, fuel cells are powering a small revolution in logistics. The next step of my journey leads me to the United Kingdom. In Oxford, I met with Joe Bamford, an entrepreneur who put forward a vision powered by hydrogen technologies. His company is making thousands of buses across the UK to further the zero-emission ambition.
What's driving me on this is to think about the world and how do you get mass adoption of zero emissions. And for me, you get mass adoption of zero emissions when it costs the same, when it does the same, and when it's as easy to fill up. It shouldn't be anything special in reality. It should be just something we do as a matter of course. We think buses are a great place to start with hydrogen. There are 40,000 buses in the UK. Battery buses will do 60% of the distance of a diesel bus, so I would imagine 30% of the UK market will go hydrogen within the next 5 years.
Joe Bamford kept telling me about the real goal. Make it as easy as possible for the user.
When it comes to zero emission, there are two zero emission solutions, batteries and hydrogen. Why do I believe that hydrogen works better? Because it does everything that we have today. Hydrogen, we can make it at a wind farm, turn water into hydrogen, stick it on a truck, deliver it to a filling station, fill a car up in 5 minutes and off we go. It just works in quite the same manner, and I think it has to be very practical, these mass adoptions. Don't try and change too much, and human behavior is the most difficult thing to change.
Going even further, I found out about another use of fuel cells that is pushing this new reality into the realm of dreams. Beyond public transport or freight, innovation has changed the lives of a small crew.
Alors Energy Observer, c'est un véritable smart grid flottant qui représente un cercle vertueux de l'énergie, associant la production d'énergie renouvelable avec la consommation de ces énergies. On stocke quotidiennement nos énergies à travers nos batteries, mais on n'en a pas beaucoup pour être léger. Et l'hydrogène sur le long terme. L'hydrogène, c'est vraiment notre prolongateur d'autonomie, c'est le couteau suisse de ces énergies renouvelables que l'on produit quotidiennement.
This is Victorien Erussard, the skipper of the Energy Observer, a vessel that launched in Saint-Malo, France in April 2017. It is the first in the world to both generate and be powered by hydrogen. Its expedition around the world provides durable solutions for energy transition.
On a joué un véritable rôle d'ambassadeur avec les médias, les industriels, les politiques et les citoyens. L'idée, c'est d'essayer d'équilibrer nos consommations énergétiques. Lorsqu'on n'a pas assez de vent, lorsqu'il fait nuit, lorsqu'il n'y a pas de soleil, on démarre notre pile à combustible qui nous permet d'aller partout autour du monde.
The crew chose hydrogen for its characteristics.
Pour moi, l'hydrogène est une solution d'avenir dans le sens où on peut stocker un maximum d'énergie dans un faible volume. Avec la mobilité des industriels sur cette production d'hydrogène et ce stockage et les différentes applications qui sont développées, je pense qu'on est sur la bonne voie.
In Wales, I spotted a unique, fierce-looking car. I met with its designer, Hugo Spowers. Hugo is a motorsport engineer who had a business designing and developing racing cars. But something always felt wrong.
And I got out of motor racing for environmental reasons, thinking that the only future for sustainable transport. Then I heard about fuel cells. And I realized that therein lay an opportunity for me because the technology existed, but we needed to build cars differently.
Hugo and his wife Fiona are the founders of the car company River Simple.
So it's not surprising that fuel cell vehicles are taking longer to come to market because it is so different to a combustion engine that it is much easier to design a car from a clean slate around the characteristics of hydrogen technology than it is to try and shoehorn the hydrogen technology into the sort of cars that we've optimized for the last 100 years around combustion engines.
I asked him the same question I asked the team at Forza. Why hydrogen?
I don't believe that there's anything that can be remotely as efficient as a hydrogen car for the sort of range to which we've become accustomed. So that's why we're developing hydrogen cars. And it wasn't until I came across fuel cell technology that I saw a sustainable powertrain on the horizon.
Hugo and his wife Fiona are dedicated to the idea of sustainable mobility.
Our purpose statement is to pursue systematically the elimination of environmental impact of personal transport. I'm very optimistic about the future of mobility. We think we're so far from a sustainable system at the moment. We need a quantum shift. I think we're going to see huge changes ahead of us, but those changes are now, I think, unstoppable.
Unstoppable. When mobility is responsible for such a large part of global carbon emissions, those changes can come fast enough. From a dedicated group of students in the Netherlands to industry experts in the UK, from buses to race cars and forklifts, initiatives everywhere are popping up as proof that transport can reinvent itself towards a new, cleaner mobility model. I really wonder if hydrogen could decarbonize other sectors too. People I've met in Tokyo, Fukushima and Nagoya told me about the vast potential of hydrogen in Japan. With such hopes for hydrogen, I wondered if it could help achieve the dream of sustainable mobility. Innovative people everywhere are driving the ambition of a clean, carbon-free future. I traveled to the Netherlands, in Delft near Rotterdam, to meet a group of passionate young students who've pioneered the hydrogen revolution in mobility. I had a moment to chat with the Forza team, a group of students who spent one full academic year working tirelessly on a pink, carbon-free hydrogen fuel cell race car. I talked to a few of them.
Alright, sounds good. Our primary goal, it goes back to our mission, which is to promote clean hydrogen technology in the transport sector. If you tone that down to kind of really why we're here, it's to race a car very fast around the track on hydrogen power.
And we race against petrol-powered cars, just normal cars, in order to show the potential that hydrogen has and the future that hydrogen has in front of it.
So who are they? Why do these students do what they do?
I just finished my bachelor's degree, but I think there are very few groups in the world that allow people of my age and experience to do what we're doing, to make a hydrogen race car within 1 year and to make it go around the track as fast as we do. It's really quite exciting stuff, and it's quite an honor to be able to be a part of this team. So that's a huge motivation.
We are a really motivated team. We are fascinated by technology. We all study it at the university here, and that makes it really, really exciting to work in this environment because motivation of others motivates you, and getting the chance to work on a real project, full scale, is just a unique experience that just gets everyone super happy about it. Although there are ups and downs, of course. It's a hard and long year, but every one of us is making the best of it.
The question that kept coming back to me was, why hydrogen? why use fuel cells in such a competitive field?
Hydrogen is something that's emerged in the past few years, and it's something that has a lot of potential.
Fuel cell technology can basically be applied to any kind of mobility. Like a race car really pushes the technology to its limits. If a fuel cell can work in a race car, it can work anywhere.
Fuel cell technology can have a wide range of applications, and I just really believe they can be widely used in the future for many, many types of applications.
The way they talked about fuel cells gave me the impression that there was some sort of higher purpose. I asked them if they felt like they were changing the world.
We're definitely putting some work into that. I mean, in the end, what we're contributing to is a much bigger vision, the electrification and the moving towards sustainable energies and sustainable technologies for the future. So in that sense, we are for sure contributing to such a vision for the future.
I think it is important that we do find an alternative to fossil fuels, and hydrogen, as I mentioned, it's becoming quite a possibility, but the only thing you can do is try. You have to try your best or else all is lost.
I was blown away by the drive and ambition of these students, the mindset of a new generation, the way they decided to take on the Goliath of climate change with their own hands. But race cars, or cars for that matter, aren't the only thing that need an update. In the US, a massive shift is on the way. In a country where retail and e-commerce are two huge pillars of the economy, change can be seen at different levels too. In warehouses where millions of items are stored, some companies have started using hydrogen fuel cell forklifts instead of gas or battery-powered alternatives. And hydrogen-fueled vans and trucks are already on the road, delivering your parcels to your door. In a way, fuel cells are powering a small revolution in logistics. The next step of my journey leads me to the United Kingdom. In Oxford, I met with Joe Bamford, an entrepreneur who put forward a vision powered by hydrogen technologies. His company is making thousands of buses across the UK to further the zero-emission ambition.
What's driving me on this is to think about the world and how do you get mass adoption of zero emissions. And for me, you get mass adoption of zero emissions when it costs the same, when it does the same, and when it's as easy to fill up. It shouldn't be anything special in reality. It should be just something we do as a matter of course. We think buses are a great place to start with hydrogen. There are 40,000 buses in the UK. Battery buses will do 60% of the distance of a diesel bus, so I would imagine 30% of the UK market will go hydrogen within the next 5 years.
Joe Bamford kept telling me about the real goal. Make it as easy as possible for the user.
When it comes to zero emission, there are two zero emission solutions, batteries and hydrogen. Why do I believe that hydrogen works better? Because it does everything that we have today. Hydrogen, we can make it at a wind farm, turn water into hydrogen, stick it on a truck, deliver it to a filling station, fill a car up in 5 minutes and off we go. It just works in quite the same manner, and I think it has to be very practical, these mass adoptions. Don't try and change too much, and human behavior is the most difficult thing to change.
Going even further, I found out about another use of fuel cells that is pushing this new reality into the realm of dreams. Beyond public transport or freight, innovation has changed the lives of a small crew.
Alors Energy Observer, c'est un véritable smart grid flottant qui représente un cercle vertueux de l'énergie, associant la production d'énergie renouvelable avec la consommation de ces énergies. On stocke quotidiennement nos énergies à travers nos batteries, mais on n'en a pas beaucoup pour être léger, et l'hydrogène sur le long terme. L'hydrogène, c'est vraiment notre prolongateur d'autonomie, c'est le couteau suisse de ces énergies renouvelables que l'on produit quotidiennement.
This is Victorien Erussard, the skipper of the Energy Observer, a vessel that launched in Saint-Malo, France in April 2017. It is the first in the world to both generate and be powered by hydrogen. Its expedition around the world provides durable solutions for energy transition.
On a joué un véritable rôle d'ambassadeur avec les médias, les industriels, les politiques et les citoyens. L'idée, c'est d'essayer d'équilibrer nos consommations énergétiques. Lorsqu'on n'a pas assez de vent, lorsqu'il fait nuit, lorsqu'il n'y a pas de soleil, on démarre notre pile à combustible qui nous permet d'aller partout autour du monde.
The crew chose hydrogen for its characteristics.
Pour moi, l'hydrogène est une solution d'avenir dans le sens où on peut stocker un maximum d'énergie dans un faible volume. Avec la mobilité des industriels sur cette production d'hydrogène et ce stockage et les différentes applications qui sont développées, je pense qu'on est sur la bonne voie.
In Wales, I spotted a unique, fierce-looking car. I met with its designer, Hugo Spowers. Hugo is a motorsport engineer who had a business designing and developing racing cars. But something always felt wrong.
And I got out of motor racing for environmental reasons, thinking that the only future for sustainable transport. Then I heard about fuel cells. And I realised that therein lay an opportunity for me because the technology existed, but we needed to build cars differently.
Hugo and his wife Fiona are the founders of the car company River Simple.
So it's not surprising that fuel cell vehicles are taking longer to come to market because it is so different to a combustion engine that it is much easier to design a car from a clean slate around the characteristics of hydrogen technology than it is to try and shoehorn the hydrogen technology into the sort of cars that we've optimized for the last 100 years around combustion engines.
I asked him the same question I asked the team at Forza. Why hydrogen?
I don't believe that there's anything that can be remotely as efficient as a hydrogen car for the sort of range to which we've become accustomed. So that's why we're developing hydrogen cars. And it wasn't until I came across fuel cell technology that I saw a sustainable powertrain on the horizon.
Hugo and his wife Fiona are dedicated to the idea of sustainable mobility.
Our purpose statement is to pursue systematically the elimination of environmental impact of personal transport. I'm very optimistic about the future of mobility. We think we're so far from a sustainable system at the moment. We need a quantum shift. I think we're going to see huge changes ahead of us, but those changes are now, I think, unstoppable.
Unstoppable. When mobility is responsible for such a large part of global carbon emissions, those changes can come fast enough. From a dedicated group of students in the Netherlands to industry experts in the UK, from buses to race cars and forklifts, initiatives everywhere are popping up as proof that transport can reinvent itself towards a new, cleaner mobility model. I really wonder if hydrogen could decarbonize other sectors too. People I've met in Tokyo, Fukushima and Nagoya told me about the vast potential of hydrogen in Japan. With such hopes for hydrogen, I wondered if it could help achieve the dream of sustainable mobility. Innovative people everywhere are driving the ambition of a clean, carbon-free future. I traveled to the Netherlands, in Delft near Rotterdam, to meet a group of passionate young students who've pioneered the hydrogen revolution in mobility. I had a moment to chat with the Forza team, a group of students who spent one full academic year working tirelessly on a pink, carbon-free hydrogen fuel cell race car. I talked to a few of them.
Alright, sounds good. Our primary goal, it goes back to our mission, which is to promote clean hydrogen technology in the transport sector. If you tone that down to kind of really why we're here, it's to race a car very fast around the track on hydrogen power.
And we race against petrol-powered cars, just normal cars, in order to show the potential that hydrogen has and the future that hydrogen has in front of it.
So who are they? Why do these students do what they do?
I just finished my bachelor's degree, but I think there are very few groups in the world that allow people of my age and experience to do what we're doing, to make a hydrogen race car within 1 year and to make it go around a track as fast as we do. It's really quite exciting stuff, and it's quite an honor to be able to be a part of this team. So that's a huge motivation.
We are a really motivated team. We are fascinated by technology. We all study it at the university here, and that makes it really, really exciting to work in this environment, because motivation of others motivates you, and getting the chance to work on a real project, full scale, is just a unique experience that just gets everyone super happy about it. Although there are ups and downs, of course. It's a hard and long year, but every one of us is making the best of it.
The question that kept coming back to me was, why hydrogen? Why use fuel cells in such a competitive field?
Hydrogen is something that's emerged in the past few years, and it's something that has a lot of potential.
Fuel cell technology can basically be applied to any kind of mobility. Like a race car really pushes the technology to its limits. If a fuel cell can work in a race car, it can work anywhere.
Fuel cell technology can have a wide range of applications, and I just really believe they can be widely used in the future for many, many types of applications.
The way they talked about fuel cells gave me the impression that there was some sort of higher purpose. I asked them if they felt like they were changing the world.
We're definitely putting some work into that. I mean, in the end, what we're contributing to is a much bigger vision, the electrification and the moving towards sustainable energies and sustainable technologies for the future. So in that sense, we are for sure contributing to such a vision for the future.
I think it is important that we do find an alternative to fossil fuels, and hydrogen, as I mentioned, it's becoming quite a possibility, but the only thing you can do is try. You have to try your best, or else all is lost.
I was blown away by the drive and ambition of these students, the mindset of a new generation, the way they decided to take on the Goliath of climate change with their own hands. But race cars, or cars for that matter, aren't the only thing that need an update. In the US, a massive shift is on the way. In a country where retail and e-commerce are two huge pillars of the economy, change can be seen at different levels too. In warehouses where millions of items are stored, some companies have started using hydrogen fuel cell forklifts instead of gas or battery-powered alternatives. And hydrogen-fueled vans and trucks are already on the road, delivering your parcels to your door. In a way, fuel cells are powering a small revolution in logistics. The next step of my journey leads me to the United Kingdom. In Oxford, I met with Joe Bamford, an entrepreneur who put forward a vision powered by hydrogen technologies. His company is making thousands of buses across the UK to further the zero-emission ambition.
What's driving me on this is to think about the world and how do you get mass adoption of zero emissions. And for me, you get mass adoption of zero emissions when it costs the same, when it does the same, and when it's as easy to fill up. It shouldn't be anything special in reality. It should be just something we do as a matter of course. We think buses are a great place to start with hydrogen. There are 40,000 buses in the UK. Battery buses will do 60% of the distance of a diesel bus, so I would imagine 30% of the UK market will go hydrogen within the next 5 years.
Joe Bamford kept telling me about the real goal: make it as easy as possible for the user.
When it comes to zero emission, there are two zero emission solutions, batteries and hydrogen. Why do I believe that hydrogen works better? Because it does everything that we have today. Hydrogen, we can make it at a wind farm, turn water into hydrogen, stick it on a truck, deliver it to a filling station, fill a car up in 5 minutes, and off we go. It just works in quite the same manner, and I think it has to be very practical, these mass adoptions. Don't try and change too much, and human behavior is the most difficult thing to change.
Going even further, I found out about another use of fuel cells that is pushing this new reality into the realm of dreams. Beyond public transport or freight, innovation has changed the lives of a small crew.
Alors Energy Observer, c'est un véritable smart grid flottant qui représente un cercle vertueux de l'énergie, associant la production d'énergie renouvelable avec la consommation de ces énergies. On stocke quotidiennement nos énergies à travers nos batteries, mais on n'en a pas beaucoup pour être léger. Et l'hydrogène sur le long terme. L'hydrogène, c'est vraiment notre prolongateur d'autonomie, c'est le couteau suisse de ces énergies renouvelables que l'on produit quotidiennement.
This is Victorien Russard, the skipper of the Energy Observer, a vessel that launched in Saint-Malo, France in April 2017. It is the first in the world to both generate and be powered by hydrogen. Its expedition around the world provides durable solutions for energy transition.
On a joué un véritable rôle d'ambassadeur avec les médias, les industriels, les politiques et les citoyens. L'idée, c'est d'essayer d'équilibrer nos consommations énergétiques. Lorsqu'on n'a pas assez de vent, lorsqu'il fait nuit, lorsqu'il n'y a pas de soleil, on démarre notre pile à combustible qui nous permet d'aller partout autour du monde.
The crew chose hydrogen for its characteristics.
Pour moi, l'hydrogène est une solution d'avenir dans le sens où on peut stocker un maximum d'énergie dans un faible volume. Avec la mobilité des industriels sur cette production d'hydrogène et ce stockage et les différentes applications qui sont développées, je pense qu'on est sur la bonne voie.
In Wales, I spotted a unique, fierce-looking car. I met with its designer, Hugo Spowers. Hugo is a motorsport engineer who had a business designing and developing racing cars. But something always felt wrong.
And I got out of motor racing for environmental reasons, thinking that the only future for sustainable transport. Then I heard about fuel cells. And I realised that therein lay an opportunity for me because the technology existed, but we needed to build cars differently.
Hugo and his wife Fiona are the founders of the car company River Simple.
So it's not surprising that fuel cell vehicles are taking longer to come to market because it is so different to a combustion engine that it is much easier to design a car from a clean slate around the characteristics of hydrogen technology than it is to try and shoehorn the hydrogen technology into the sort of cars that we've optimized for the last 100 years around combustion engines.
I asked him the same question I asked the team at Forza. Why hydrogen?
I don't believe that there's anything that can be remotely as efficient as a hydrogen car for the sort of range to which we've become accustomed. So that's why we're developing hydrogen cars. And it wasn't until I came across fuel cell technology that I saw a sustainable powertrain on the horizon.
Hugo and his wife Fiona are dedicated to the idea of sustainable mobility.
Our purpose statement is to pursue systematically the elimination of environmental impact of personal transport. I'm very optimistic about the future of mobility. We think we're so far from a sustainable system at the moment. We need a quantum shift. I think we're going to see huge changes ahead of us. But those changes are now, I think, unstoppable.
Unstoppable. When mobility is responsible for such a large part of global carbon emissions, those changes can come fast enough. From a dedicated group of students in the Netherlands to industry experts in the UK, from buses to race cars and forklifts, initiatives everywhere are popping up as proof that transport can reinvent itself towards a new, cleaner mobility model. I really wonder if hydrogen could decarbonize other sectors too. People I've met in Tokyo, Fukushima and Nagoya told me about the vast potential of hydrogen in Japan. With such hopes for hydrogen, I wondered if it could help achieve the dream of sustainable mobility. Innovative people everywhere are driving the ambition of a clean, carbon-free future. I traveled to the Netherlands, in Delft near Rotterdam, to meet a group of passionate young students who've pioneered the hydrogen revolution in mobility. I had a moment to chat with the Forza team, a group of students who spent one full academic year working tirelessly on a pink, carbon-free hydrogen fuel cell race car. I talked to a few of them.
Alright, sounds good. Our primary goal, it goes back to our mission, which is to promote clean hydrogen technology in the transport sector. If you tone that down to kind of really why we're here, it's to race a car very fast around the track on hydrogen power.
And we race against petrol-powered cars, just normal cars, in order to show the potential that hydrogen has and the future that hydrogen has in front of it.
So who are they? Why do these students do what they do?
I just finished my bachelor's degree, but I think there are very few groups in the world that allow people of my age and experience to do what we're doing, to make a hydrogen race car within 1 year and to make it go around the track as fast as we do. It's really quite exciting stuff, and it's quite an honor to be able to be a part of this team. So that's a huge motivation.
We are a really motivated team. We are fascinated by technology. We all study it at the university here, and that makes it really, really exciting to work in this environment, because motivation of others motivates you, and getting the chance to work on a real project, full scale, is just a unique experience that just gets everyone super happy about it. Although there are ups and downs, of course. It's a hard and long year, but every one of us is making the best of it.
The question that kept coming back to me was, why hydrogen? Why use fuel cells in such a competitive field?
Hydrogen is something that's emerged in the past few years, and it's something that has a lot of potential.
Fuel cell technology can basically be applied to any kind of mobility. Like a race car really pushes the technology to its limits. If a fuel cell can work in a race car, it can work anywhere.
Fuel cell technology can have a wide range of applications, and I just really believe they can be widely used in the future for many, many types of applications.
The way they talked about fuel cells gave me the impression that there was some sort of higher purpose. I asked them if they felt like they were changing the world.
We're definitely putting some work into that. I mean, in the end, what we're contributing to is a much bigger vision, the electrification and the moving towards sustainable energies and sustainable technologies for the future. So in that sense, we are for sure contributing to such a vision for the future.
I think it is important that we do find an alternative to fossil fuels, and hydrogen, as I mentioned, it's becoming quite a possibility, but the only thing you can do is try. You have to try your best, or else all is lost.
I was blown away by the drive and ambition of these students, the mindset of a new generation, the way they decided to take on the Goliath of climate change with their own hands. But race cars, or cars for that matter, aren't the only thing that need an update. In the US, a massive shift is on the way. In a country where retail and e-commerce are two huge pillars of the economy, change can be seen at different levels too. In warehouses where millions of items are stored, some companies have started using hydrogen fuel cell forklifts instead of gas or battery-powered alternatives. And hydrogen-fueled vans and trucks are already on the road, delivering your parcels to your door. In a way, fuel cells are powering a small revolution in logistics. The next step of my journey leads me to the United Kingdom. In Oxford, I met with Joe Bamford, an entrepreneur who put forward a vision powered by hydrogen technologies. His company is making thousands of buses across the UK to further the zero-emission ambition.
What's driving me on this is to think about the world and how do you get mass adoption of zero emissions. And for me, you get mass adoption of zero emissions when it costs the same, when it does the same, and when it's as easy to fill up. It shouldn't be anything special in reality. It should be just something we do as a matter of course. We think buses are a great place to start with hydrogen. There are 40,000 buses in the UK. Battery buses will do 60% of the distance of a diesel bus, so I would imagine 30% of the UK market will go hydrogen within the next 5 years.
Joe Bamford kept telling me about the real goal: make it as easy as possible for the user.
When it comes to zero emission, there are two zero emission solutions, batteries and hydrogen. Why do I believe that hydrogen works better? Because it does everything that we have today. Hydrogen, we can make it at a wind farm, turn water into hydrogen, stick it on a truck, deliver it to a filling station, fill a car up in 5 minutes and off we go. It just works in quite the same manner, and I think it has to be very practical, these mass adoptions. Don't try and change too much, and human behavior is the most difficult thing to change.
Going even further, I found out about another use of fuel cells that is pushing this new reality into the realm of dreams. Beyond public transport or freight, innovation has changed the lives of a small crew.
Alors Energy Observer, c'est un véritable smart grid flottant qui représente un cercle vertueux de l'énergie, associant la production d'énergie renouvelable avec la consommation de ces énergies. On stocke quotidiennement nos énergies à travers nos batteries, mais on n'en a pas beaucoup pour être léger, et l'hydrogène sur le long terme. L'hydrogène, c'est vraiment notre prolongateur d'autonomie, c'est le couteau suisse de ces énergies renouvelables que l'on produit quotidiennement.
This is Victorien Erussard, the skipper of the Energy Observer, a vessel that launched in Saint-Malo, France in April 2017. It is the first in the world to both generate and be powered by hydrogen. Its expedition around the world provides durable solutions for energy transition.
On a joué un véritable rôle d'ambassadeur avec les médias, les industriels, les politiques et les citoyens. L'idée, c'est d'essayer d'équilibrer nos consommations énergétiques. Lorsqu'on n'a pas assez de vent, lorsqu'il fait nuit, lorsqu'il n'y a pas de soleil, on démarre notre pile à combustible qui nous permet d'aller partout autour du monde.
The crew chose hydrogen for its characteristics.
Pour moi, l'hydrogène est une solution d'avenir dans le sens où on peut stocker un maximum d'énergie dans un faible volume. Avec la mobilité des industriels sur cette production d'hydrogène et ce stockage et les différentes applications qui sont développées, je pense qu'on est sur la bonne voie.
In Wales, I spotted a unique, fierce-looking car. I met with its designer, Hugo Spowers. Hugo is a motorsport engineer who had a business designing and developing racing cars. But something always felt wrong.
And I got out of motor racing for environmental reasons, thinking that the only future for sustainable transport. Then I heard about fuel cells. And I realised that therein lay an opportunity for me because the technology existed, but we needed to build cars differently.
Hugo and his wife Fiona are the founders of the car company River Simple.
So it's not surprising that fuel cell vehicles are taking longer to come to market because it is so different to a combustion engine that it is much easier to design a car from a clean slate around the characteristics of hydrogen technology than it is to try and shoehorn the hydrogen technology into the sort of cars that we've optimized for the last 100 years around combustion engines.
I asked him the same question I asked the team at Forza. Why hydrogen?
I don't believe that there's anything that can be remotely as efficient as a hydrogen car for the sort of range to which we've become accustomed. So that's why we're developing hydrogen cars. And it wasn't until I came across fuel cell technology that I saw a sustainable powertrain on the horizon.
Hugo and his wife Fiona are dedicated to the idea of sustainable mobility.
Our purpose statement is to pursue systematically the elimination of environmental impact of personal transport. I'm very optimistic about the future of mobility. We think we're so far from a sustainable system at the moment. We need a quantum shift. I think we're going to see huge changes ahead of us, but those changes are now, I think, unstoppable.
Unstoppable. When mobility is responsible for such a large part of global carbon emissions, those changes can come fast enough. From a dedicated group of students in the Netherlands to industry experts in the UK, from buses to race cars and forklifts, initiatives everywhere are popping up as proof that transport can reinvent itself towards a new, cleaner mobility model. I really wonder if hydrogen could decarbonize other sectors too. people I've met in Tokyo, Fukushima and Nagoya told me about the vast potential of hydrogen in Japan. With such hopes for hydrogen, I wondered if it could help achieve the dream of sustainable mobility. Innovative people everywhere are driving the ambition of a clean, carbon-free future. I traveled to the Netherlands, in Delft near Rotterdam, to meet a group of passionate young students who've pioneered the hydrogen revolution in mobility. I had a moment to chat with the Forza team, a group of students who spent one full academic year working tirelessly on a pink, carbon-free hydrogen fuel cell race car. I talked to a few of them.
Alright, sounds good. Our primary goal, it goes back to our mission, which is to promote clean hydrogen technology in the transport sector. If you tone that down to kind of really why we're here, it's to race a car very fast around the track on hydrogen power.
And we race against petrol-powered cars, just normal cars, in order to show the potential that hydrogen has and the future that hydrogen has in front of it.
So who are they? Why do these students do what they do?
I just finished my bachelor's degree, but I think there are very few groups in the world that allow people of my age and experience to do what we're doing, to make a hydrogen race car within 1 year and to make it go around a track as fast as we do. It's really quite exciting stuff. And it's quite an honor to be able to be a part of this team. So that's a huge motivation.
We are a really motivated team. We are fascinated by technology. We all study it at the university here, and that makes it really, really exciting to work in this environment, because motivation of others motivates you, and getting the chance to work on a real project, full scale, is just a unique experience that just gets everyone super happy about it. Although there are ups and downs, of course. It's a hard and long year, but every one of us is making the best of it.
The question that kept coming back to me was, why hydrogen? Why use fuel cells in such a competitive field?
Hydrogen is something that's emerged in the past few years, and it's something that has a lot of potential.
Fuel cell technology can basically be applied to any kind of mobility. Like a race car really pushes the technology to its limits. If a fuel cell can work in a race car, it can work anywhere.
Fuel cell technology can have a wide range of applications, and I just really believe they can be widely used in the future for many, many types of applications.
The way they talked about fuel cells gave me the impression that there was some sort of higher purpose. I asked them if they felt like they were changing the world.
We're definitely putting some work into that. I mean, in the end, what we're contributing to is a much bigger vision, the electrification and the moving towards sustainable energies and sustainable technologies for the future. So in that sense, we are for sure contributing to such a vision for the future.
I think it is important that we do find an alternative to fossil fuels, and hydrogen, as I mentioned, it's becoming quite a possibility, but the only thing you can do is try. You have to try your best, or else all is lost.
I was blown away by the drive and ambition of these students, the mindset of a new generation, the way they decided to take on the Goliath of climate change with their own hands. But race cars, or cars for that matter, aren't the only thing that need an update. In the US, a massive shift is on the way. In a country where retail and e-commerce are two huge pillars of the economy, change can be seen at different levels too. In warehouses where millions of items are stored, some companies have started using hydrogen fuel cell forklifts instead of gas or battery-powered alternatives. And hydrogen-fueled vans and trucks are already on the road, delivering your parcels to your door. In a way, fuel cells are powering a small revolution in logistics. The next step of my journey leads me to the United Kingdom. In Oxford, I met with Joe Bamford, an entrepreneur who put forward a vision powered by hydrogen technologies. His company is making thousands of buses across the UK to further the zero-emission ambition.
What's driving me on this is to think about the world and how do you get mass adoption of zero emissions. And for me, you get mass adoption of zero emissions when it costs the same, when it does the same, and when it's as easy to fill up. It shouldn't be anything special in reality. It should be just something we do as a matter of course. We think buses are a great place to start with hydrogen. There are 40,000 buses in the UK. Battery buses will do 60% of the distance of a diesel bus, so I would imagine 30% of the UK market will go hydrogen within the next 5 years.
Joe Bamford kept telling me about the real goal. Make it as easy as possible for the user.
When it comes to zero emission, there are two zero emission solutions, batteries and hydrogen. Why do I believe that hydrogen works better? Because it does everything that we have today. Hydrogen, we can make it as a wind farm, turn water into hydrogen, stick it on a truck, deliver it to a filling station, fill a car up in 5 minutes and off we go. It just works in quite the same manner, and I think it has to be very practical, these mass adoptions. Don't try and change too much, and human behavior is the most difficult thing to change.
Going even further, I found out about another use of fuel cells that is pushing this new reality into the realm of dreams. Beyond public transport or freight, innovation has changed the lives of a small crew.
Alors Energy Observer, c'est un véritable smart grid flottant qui représente un cercle vertueux de l'énergie, associant la production d'énergie renouvelable avec la consommation de ces énergies. On stocke quotidiennement nos énergies à travers nos batteries, mais on n'en a pas beaucoup pour être léger. Et l'hydrogène sur le long terme. L'hydrogène, c'est vraiment notre prolongateur d'autonomie, c'est le couteau suisse de ces énergies renouvelables que l'on produit quotidiennement.
This is Victorien Erussard, the skipper of the Energy Observer, a vessel that launched in Saint-Malo, France in April 2017. It is the first in the world to both generate and be powered by hydrogen. Its expedition around the world provides durable solutions for energy transition.
On a joué un véritable rôle d'ambassadeur avec les médias, les industriels, les politiques et les citoyens. L'idée, c'est d'essayer d'équilibrer nos consommations énergétiques. Lorsqu'on n'a pas assez de vent, lorsqu'il fait nuit, lorsqu'il n'y a pas de soleil, on démarre notre pile à combustible qui nous permet d'aller partout autour du monde.
The crew chose hydrogen for its characteristics.
Pour moi, l'hydrogène est une solution d'avenir dans le sens où on peut stocker un maximum d'énergie dans un faible volume. Avec la mobilité des industriels sur cette production d'hydrogène et ce stockage et les différentes applications qui sont développées, je pense qu'on est sur la bonne voie.
In Wales, I spotted a unique, fierce-looking car. I met with its designer, Hugo Spowers. Hugo is a motorsport engineer who had a business designing and developing racing cars. But something always felt wrong.
And I got out of motor racing for environmental reasons, thinking that the only future for sustainable transport. Then I heard about fuel cells. And I realised that therein lay an opportunity for me because the technology existed, but we needed to build cars differently.
Hugo and his wife Fiona are the founders of the car company River Simple.
So it's not surprising that fuel cell vehicles are taking longer to come to market because it is so different to a combustion engine that it is much easier to design a car from a clean slate around the characteristics of hydrogen technology than it is to try and shoehorn the hydrogen technology into the sort of cars that we've optimized for the last 100 years around combustion engines.
I asked him the same question I asked the team at Forza. Why hydrogen?
I don't believe that there's anything that can be remotely as efficient as a hydrogen car for the sort of range to which we've become accustomed. So that's why we're developing hydrogen cars. And it wasn't until I came across fuel cell technology that I saw a sustainable powertrain on the horizon.
Hugo and his wife Fiona are dedicated to the idea of sustainable mobility.
Our purpose statement is to pursue systematically the elimination of environmental impact of personal transport. I'm very optimistic about the future of mobility. We think we're so far from a sustainable system at the moment. We need a quantum shift. I think we're going to see huge changes ahead of us, but those changes are now, I think, unstoppable.
Unstoppable. When mobility is responsible for such a large part of global carbon emissions, those changes can come fast enough. From a dedicated group of students in the Netherlands to industry experts in the UK, from buses to race cars and forklifts, initiatives everywhere are popping up as proof that transport can reinvent itself towards a new, cleaner mobility model. I really wonder if hydrogen could decarbonize other sectors too. People I've met in Tokyo, Fukushima and Nagoya told me about the vast potential of hydrogen in Japan. With such hopes for hydrogen, I wondered if it could help achieve the dream of sustainable mobility. Innovative people everywhere are driving the ambition of a clean, carbon-free future. I traveled to the Netherlands, in Delft near Rotterdam, to meet a group of passionate young students who've pioneered the hydrogen revolution in mobility. I had a moment to chat with the Forza team, a group of students who spent one full academic year working tirelessly on a pink, carbon-free hydrogen fuel cell race car. I talked to a few of them.
Alright, sounds good. Our primary goal, it goes back to our mission, which is to promote clean hydrogen technology in the transport sector. If you tone that down to kind of really why we're here, it's to race a car very fast around the track on hydrogen power.
And we race against petrol-powered cars, just normal cars, in order to show the potential that hydrogen has and the future that hydrogen has in front of it.
So who are they? Why do these students do what they do?
I just finished my bachelor's degree, but I think there are very few groups in the world that allow people of my age and experience to do what we're doing, to make a hydrogen race car within 1 year and to make it go around a track as fast as we do. It's really quite exciting stuff, and it's quite an honor to be able to be a part of this team. So that's a huge motivation.
We are a really motivated team. We are fascinated by technology. We all study it at the university here, and that makes it really, really exciting to work in this environment, because motivation of others motivates you, and getting the chance to work on a real project, full scale, is just a unique experience that just gets everyone super happy about it. Although there are ups and downs, of course. It's a hard and long year, but every one of us is making the best of it.
The question that kept coming back to me was, why hydrogen? Why use fuel cells in such a competitive field?
Hydrogen is something that's emerged in the past few years, and it's something that has a lot of potential.
Fuel cell technology can basically be applied to any kind of mobility. Like a race car really pushes the technology to its limits. If a fuel cell can work in a race car, it can work anywhere.
Fuel cell technology can have a wide range of applications, and I just really believe they can be widely used in the future for many, many types of applications.
The way they talked about fuel cells gave me the impression that there was some sort of higher purpose. I asked them if they felt like they were changing the world.
We're definitely putting some work into that. I mean, in the end, what we're contributing to is a much bigger vision, the electrification and the moving towards sustainable energies and sustainable technologies for the future. So in that sense, we are for sure contributing to such a vision for the future.
I think it is important that we do find an alternative to fossil fuels, and hydrogen, as I mentioned, it's becoming quite a possibility, but the only thing you can do is try. You have to try your best, or else all is lost.
I was blown away by the drive and ambition of these students, the mindset of a new generation, the way they decided to take on the Goliath of climate change with their own hands. But race cars, or cars for that matter, aren't the only thing that need an update. In the US, a massive shift is on the way. In a country where retail and e-commerce are two huge pillars of the economy, change can be seen at different levels too. In warehouses where millions of items are stored, some companies have started using hydrogen fuel cell forklifts instead of gas or battery-powered alternatives. And hydrogen-fueled vans and trucks are already on the road, delivering your parcels to your door. In a way, fuel cells are powering a small revolution in logistics. The next step of my journey leads me to the United Kingdom. In Oxford, I met with Joe Bamford, an entrepreneur who put forward a vision powered by hydrogen technologies. His company is making thousands of buses across the UK to further the zero-emission ambition.
What's driving me on this is to think about the world and how do you get mass adoption of zero emissions. And for me, you get mass adoption of zero emissions when it costs the same, when it does the same, and when it's as easy to fill up. It shouldn't be anything special in reality. It should be just something we do as a matter of course. We think buses are a great place to start with hydrogen. There are 40,000 buses in the UK. Battery buses will do 60% of the distance of a diesel bus, so I would imagine 30% of the UK market will go hydrogen within the next 5 years.
Joe Bamford kept telling me about the real goal. Make it as easy as possible for the user.
When it comes to zero emission, there are two zero emission solutions, batteries and hydrogen. Why do I believe that hydrogen works better? Because it does everything that we have today. Hydrogen, we can make it at a wind farm, turn water into hydrogen, stick it on a truck, deliver it to a filling station, fill a car up in 5 minutes and off we go. It just works in quite the same manner, and I think it has to be very practical, these mass adoptions. Don't try and change too much, and human behavior is the most difficult thing to change.
Going even further, I found out about another use of fuel cells that is pushing this new reality into the realm of dreams. Beyond public transport or freight, innovation has changed the lives of a small crew.
Alors Energy Observer, c'est un véritable smart grid flottant qui représente un cercle vertueux de l'énergie, associant la production d'énergie renouvelable avec la consommation de ces énergies. On stocke quotidiennement nos énergies à travers nos batteries, mais on n'en a pas beaucoup pour être léger, et l'hydrogène sur le long terme. L'hydrogène, c'est vraiment notre prolongateur d'autonomie, c'est le couteau suisse de ces énergies renouvelables que l'on produit quotidiennement.
This is Victorien Erussard, the skipper of the Energy Observer, a vessel that launched in Saint-Malo, France in April 2017. It is the first in the world to both generate and be powered by hydrogen. Its expedition around the world provides durable solutions for energy transition.
On a joué un véritable rôle d'ambassadeur avec les médias, les industriels, les politiques et les citoyens. L'idée, c'est d'essayer d'équilibrer nos consommations énergétiques. Lorsqu'on n'a pas assez de vent, lorsqu'il fait nuit, lorsqu'il n'y a pas de soleil, on démarre notre pile à combustible qui nous permet d'aller partout autour du monde.
The crew chose hydrogen for its characteristics.
Pour moi, l'hydrogène est une solution d'avenir dans le sens où on peut stocker un maximum d'énergie dans un faible volume. Avec la mobilité des industriels sur cette production d'hydrogène et ce stockage et les différentes applications qui sont développées, je pense qu'on est sur la bonne voie.
In Wales, I spotted a unique, fierce-looking car. I met with its designer, Hugo Spowers. Hugo is a motorsport engineer who had a business designing and developing racing cars. But something always felt wrong.
And I got out of motor racing for environmental reasons, thinking that the only future for sustainable transport. Then I heard about fuel cells. And I realised that therein lay an opportunity for me because the technology existed, but we needed to build cars differently.
Hugo and his wife Fiona are the founders of the car company River Simple.
So it's not surprising that fuel cell vehicles are taking longer to come to market because it is so different to a combustion engine that it is much easier to design a car from a clean slate around the characteristics of hydrogen technology than it is to try and shoehorn the hydrogen technology into the sort of cars that we've optimized for the last 100 years around combustion engines.
I asked him the same question I asked the team at Forza. Why hydrogen?
I don't believe that there's anything that can be remotely as efficient as a hydrogen car for the sort of range to which we've become accustomed. So that's why we're developing hydrogen cars. And it wasn't until I came across fuel cell technology that I saw a sustainable powertrain on the horizon.
Hugo and his wife Fiona are dedicated to the idea of sustainable mobility.
Our purpose statement is to pursue systematically the elimination of environmental impact of personal transport. I'm very optimistic about the future of mobility. We think we're so far from a sustainable system at the moment. We need a quantum shift. I think we're going to see huge changes ahead of us, but those changes are now, I think, unstoppable.
Unstoppable. When mobility is responsible for such a large part of global carbon emissions, those changes can come fast enough. From a dedicated group of students in the Netherlands to industry experts in the UK, from buses to race cars and forklifts, initiatives everywhere are popping up as proof that transport can reinvent itself towards a new, cleaner mobility model. I really wonder if hydrogen could decarbonize other sectors too. People I've met in Tokyo, Fukushima and Nagoya told me about the vast potential of hydrogen in Japan. With such hopes for hydrogen, I wondered if it could help achieve the dream of sustainable mobility. Innovative people everywhere are driving the ambition of a clean, carbon-free future. I traveled to the Netherlands, in Delft near Rotterdam, to meet a group of passionate young students who've pioneered the hydrogen revolution in mobility. I had a moment to chat with the Forza team, a group of students who spent one full academic year working tirelessly on a pink, carbon-free hydrogen fuel cell race car. I talked to a few of them.
Alright, sounds good. Our primary goal, it goes back to our mission, which is to promote clean hydrogen technology in the transport sector. If you tone that down to kind of really why we're here, it's to race a car very fast around the track on hydrogen power.
And we race against petrol-powered cars, just normal cars, in order to show the potential that hydrogen has and the future that hydrogen has in front of it.
So who are they? Why do these students do what they do?
I just finished my bachelor's degree, but I think there are very few groups in the world that allow people of my age and experience to do what we're doing, to make a hydrogen race car within 1 year and to make it go around a track as fast as we do. It's really quite exciting stuff, and it's quite an honor to be able to be a part of this team. So that's a huge motivation.
We are a really motivated team. We are fascinated by technology. We all study it at the university here, and that makes it really, really exciting to work in this environment, because motivation of others motivates you, and getting the chance to work on a real project, full scale, is just a unique experience that just gets everyone super happy about it. Although there are ups and downs, of course. It's a hard and long year, but every one of us is making the best of it.
The question that kept coming back to me was, why hydrogen? Why use fuel cells in such a competitive field?
Hydrogen is something that's emerged in the past few years, and it's something that has a lot of potential.
Fuel cell technology can basically be applied to any kind of mobility. Like a race car really pushes the technology to its limits. If a fuel cell can work in a race car, it can work anywhere.
Fuel cell technology can have a wide range of applications, and I just really believe they can be widely used in the future for many, many types of applications.
The way they talked about fuel cells gave me the impression that there was some sort of higher purpose. I asked them if they felt like they were changing the world.
we're definitely putting some work into that. I mean, in the end, what we're contributing to is a much bigger vision, the electrification and the moving towards sustainable energies and sustainable technologies for the future. So in that sense, we are for sure contributing to such a vision for the future.
I think it is important that we do find an alternative to fossil fuels, and hydrogen, as I mentioned, it's becoming quite a possibility, but the only thing you can do is try. You have to try your best or else all is lost.
I was blown away by the drive and ambition of these students, the mindset of a new generation, the way they decided to take on the Goliath of climate change with their own hands. But race cars, or cars for that matter, aren't the only thing that need an update. In the US, a massive shift is on the way. In a country where retail and e-commerce are two huge pillars of the economy, change can be seen at different levels too. In warehouses where millions of items are stored, some companies have started using hydrogen fuel cell forklifts instead of gas or battery-powered alternatives. And hydrogen-fueled vans and trucks are already on the road, delivering your parcels to your door. In a way, fuel cells are powering a small revolution in logistics. The next step of my journey leads me to the United Kingdom. In Oxford, I met with Joe Bamford, an entrepreneur who put forward a vision powered by hydrogen technologies. His company is making thousands of buses across the UK to further the zero-emission ambition.
What's driving me on this is to think about the world and how do you get mass adoption of zero emissions. And for me, you get mass adoption of zero emissions when it costs the same, when it does the same, and when it's as easy to fill up. It shouldn't be anything special in reality. It should be just something we do as a matter of course. We think buses are a great place to start with hydrogen. There are 40,000 buses in the UK. Battery buses will do 60% of the distance of a diesel bus, so I would imagine 30% of the UK market will go hydrogen within the next 5 years.
Joe Bamford kept telling me about the real goal. Make it as easy as possible for the user.
When it comes to zero emission, there are two zero emission solutions, batteries and hydrogen. Why do I believe that hydrogen works better? Because it does everything that we have today. Hydrogen, we can make it at a wind farm, turn water into hydrogen, stick it on a truck, deliver it to a filling station, fill a car up in 5 minutes and off we go. It just works in quite the same manner, and I think it has to be very practical, these mass adoptions. Don't try and change too much, and human behavior is the most difficult thing to change.
Going even further, I found out about another use of fuel cells that is pushing this new reality into the realm of dreams. Beyond public transport or freight, innovation has changed the lives of a small crew.
Alors Energy Observer, c'est un véritable smart grid flottant qui représente un cercle vertueux de l'énergie, associant la production d'énergie renouvelable avec la consommation de ces énergies. On stocke quotidiennement nos énergies à travers nos batteries, mais on n'en a pas beaucoup pour être léger. Et l'hydrogène sur le long terme. L'hydrogène, c'est vraiment notre prolongateur d'autonomie, c'est le couteau suisse de ces énergies renouvelables que l'on produit quotidiennement.
This is Victorien Russard, the skipper of the Energy Observer, a vessel that launched in Saint-Malo, France in April 2017. It is the first in the world to both generate and be powered by hydrogen. Its expedition around the world provides durable solutions for energy transition.
On a joué un véritable rôle d'ambassadeur avec les médias, les industriels, les politiques et les citoyens. L'idée, c'est d'essayer d'équilibrer nos consommations énergétiques. Lorsqu'on n'a pas assez de vent, lorsqu'il fait nuit, lorsqu'il n'y a pas de soleil, on démarre notre pile à combustible qui nous permet d'aller partout autour du monde.
The crew chose hydrogen for its characteristics.
Pour moi, l'hydrogène est une solution d'avenir dans le sens où on peut stocker un maximum d'énergie dans un faible volume. Avec la mobilité des industriels sur cette production d'hydrogène et ce stockage et les différentes applications qui sont développées, je pense qu'on est sur la bonne voie.
In Wales, I spotted a unique, fierce-looking car. I met with its designer, Hugo Spowers. Hugo is a motorsport engineer who had a business designing and developing racing cars. But something always felt wrong.
And they got out.
Good afternoon, everybody. Welcome back to this last parallel session of the PRD of this year. We are facing ahead of us a very interesting set of projects that are going to tell us all about hydrogen distribution and carriers. Remember that after this, we have still another presentation for the Clean Hydrogen Partnership, and of course, don't leave the event because then we will have our awards. But now let's focus on the projects ahead of us. We have very interesting projects. The first one, because I don't want to take the time from them, is HyCare, where the University of Torino and Marcelo Barrico as the main coordinator are going to tell us all about hydrogen storage in metal hydrates. Marcelo, the floor is yours.
Okay, thank you very much indeed, Enrique, for this presentation. So it's a pleasure for me to present this HyCare project, and I like to start with a short video.
The storage of renewable energies is still a big problem because actually the production of energy from renewables is changing over time. Hydrogen can be a solution, and HyCare actually have the goal to store energy from renewable through hydrogen. For the first time in Europe, we are planning to set up a hydrogen tank that is able to store 50 kilos of hydrogen, but the very new innovation is the use of a combination of metal hydride with phase change material. This will allow to save energy and to improve the efficiency of the whole storage system. This is a real innovation for Europe.
Okay, thank you. So I just like to show a very quick project overview. You can see on the screen the different partners of this project. They are distributed among Italy, France, Germany, and we have also a contribution from Norway. The total amount of the project is about 2 million euros, and this is a list of the partners. But let me start with the main goals of this HyCare project. At the end of the day, the goal is to store hydrogen into metal hydrides, and the big issue is to try to store a huge quantity of hydrogen for metal hydride that is around 50 kilos. And there is an innovative concept to follow in this specific case, and the goal at the end of the project is to integrate this hydrogen storage system in the frame between an electrolyzer and the fuel cell. There are other different goals, but let me just move to the main concept for our project. So at the end of the day, because we know that in charging and discharging hydrogen from metal hydrides, you have an heat evolution and needs of heat, the idea is to improve the efficiency of the system, coupling the metal hydride tank with the heat storage tank. And we use a phase change material in order to store the heat that is produced during the absorption. And in the meantime, when we want hydrogen back, we use the heat from the phase change material and we drive it to the metal hydride system. So at the end of the day, the concept is rather simple. The big issue is to try to implement it into a real equipment. But let me just try to show what are the situation, what is the result that has been reached now. The first point is we already selected the alloy. It is based on iron titanium system, and the big issue is to play in such a condition, so very low temperature, very low pressure. And this, in some sense, is the main goal of the project itself. You can see that at the end of the day, looking to the figure on the bottom left, you have to manage temperature, pressure and capacity of the system. And this, if you want, is the main challenge of the project. But when the alloy is selected, then we can move in trying to implement it in the real system. The goal is to produce a huge amount of powder. The goal is to produce about 4 tons of powder, and they have compressed in pellets, as you can see in the screen. And then we already have a prototype system that is playing with a smaller amount of hydrogen, but the main goal at the end of the day is to reach 50 kilos of hydrogen managed by this system. So what you can see there is just the subunits of the whole system that we plan to produce at the end of the story. But of course, one of the key issues is to improve the efficiency. So at the end of the day, this coupling with the PCM is the big effort. And you can see in the slides that the goal is to reach a sort of high efficiency, higher than 70%. And of course, the goal is to reduce as much as possible the needs of energy from outside, so that the whole system is included in itself. Okay, so let's just quick have a look to the integration of the system. Then you can see on the screen, the idea is to have in the side of the container both the tank that is playing with the metal hydride and the tank that is playing with the PCM. Everything is very well integrated, and the goal is to have electrolyzer in one side and the fuel cell on the other one. And the goal at the end of the day is to have the single system very well organized in its own frame. Okay, so that's basically the main ideas of the project. I just like to highlight that, of course, we are very much engaged in looking to possible exploitation of the system. We receive a lot of support from different, let's say, services that are available. I like to mention this SSERR that is very useful in order to help us in how to implement the whole system. And now we are moving to the booster, but at the end of the day, all the support are very important for the project. On the right, I just like to highlight that, of course, we try to understand what is the impact of the solution. So there is an LCA activity running. This is one of the goal of the system. And of course, we have to manage also the techno-economical analysis of the whole system in order to monitor how the system can play. And in this sense, the exercise that we are doing through Trust is very, very much helping. Okay, so let me just go to the conclusion of this short description. Simply to say that, of course, we are very much engaged in dissemination activity. So we are, of course, on Twitter, LinkedIn, and YouTube. So any like for the project, any support for the project is very, very much welcome. Eric, I think that's basically it for our project. So ready to answer to any question or curiosity.
Perfect. Thank you, Marcelo, for this very nice explanation. Regarding the questions, I have to remind everybody that we will have the questions at the end of the sessions. You can see by your screen an Ask a Question button, so hopefully you can type your questions there for everybody, and we will receive them and answer them. Hopefully all of them, but let's see how many we get at the end of the session. Now, thank you for this nice presentation. We're going to move on in the storage and distribution channel or chain, and we're going to go to a project, HyGrid, a very nice project managed by the Technical University of Eindhoven. Fausto Gaiusi is going to tell us all about it, and it's basically about purification, if I understood correctly, of low concentration hydrogen streams, so that we can move the hydrogen mixed with something, let me guess natural gas, and then we can take it out where we need it. But please tell us all about it right now, Fausto. The floor is yours.
Thank you very much for the introduction. Indeed, I'm coordinating the HyGrid project, and the HyGrid is recovering hydrogen from natural gas grid. There were several projects on injecting the hydrogen. We want to make sure that we can recover the hydrogen from the natural gas grid. So the call was in 2015 and was about recovering of hydrogen from low concentration, and basically what we decide to do is to recover from natural gas grid where maximum 10% of hydrogen is present. It's a relatively long project, especially because of some problem we got during the project and because of COVID. We are now in the last phase of the project. The project is worth more than €3 million, and part of it is covered by the Switzerland, because we have a partner from Switzerland. So what you see here is the description of the project. What is important is that we look at low concentration of hydrogen, maximum 10%. The main core of the project is membrane separation, and then we also couple electrochemical separation and TSA, just to increase the purity and decrease the cost of the separation. And what we want to do is to first try a TRL 5 at a scale of around 25 kilo per day. And these are the efficiencies and costs that we have to target. Now, if you look at the project itself, it has to integrate membrane modules, electrochemical separation, and TSA. To be noted that the electrochemical separation is very similar to the electrochemical hydrogen compressor, but we use it for separation. And I put here as only three different steps, because, of course, you can integrate in different ways. What is important is that the hydrogen at the end of the day is pure enough to be used in a fuel cell, and the methane has the same pressure such that can be injected back in the grid. Now, if we look at the partners, we have partners from Netherlands, Spain, Italy, and Switzerland. Unfortunately, one of the partner sites during the project was bought by a US company, so that means that the partner was terminated during the project, and this is part of the delay that we accumulated. Now, if we look at what we are doing, I want to show you a few pictures of what we did. The main core is membranes, as I said. We produce, in this particular case, palladium membranes for the prototype, but at lab scale we also tested different membranes. And here you see a few membranes produced by Tecnalia, integrated at TUE, and then the prototype, and of course the prototype after insulation. Good news is that basically we tested the prototype at lab scale. We moved the prototype to IEA for integration, and after integration, the selectivity is still the same. So we are ready to now test in the complete system. The other point is the electrochemical separator. Most of you probably are familiar with electrochemical compressor. As I said, here we want to do the separation, and what is important is that the methane doesn't have a big pressure drop. So a lot of time was spent to keep the pressure drop below 100 millibar. And here you see a picture of the system and another picture of the complete system with the control part. And this is to be shipped this week to IGEA by IET. They are close to each other, so I think the shipping will take more or less half an hour. And then we'll be ready for integration as well. And finally, the integration itself. What we have is a membrane separator. What we do is that most of the hydrogen is separated through the membrane, then purified with the TSA, and the remaining hydrogen is separated by the electrochemical separator. This is only one of the configurations. I will show you some results later. It's a TRL 5, so we had also space for more fundamental research. As I said, the core is membranes, so we tested several types of membranes, palladium, carbon, and combination of the two. And what is nice is that if you look at low pressure region, of course, it's very difficult to reach the purity of palladium. But if you go to very high pressure, and some of the natural gas grids are at high pressure, then even membranes with low selectivity are good enough to go from less than 10%, what you have in the feed, up to more than 99% purity. And then, of course, the final purification is much easier. So a few takeaway messages. The carbon membranes are very nice because are cheap. They have no concentration polarization. They have similar purity when you go to very high pressure, but you don't need to go to high temperature, which is also good for efficiency. And at the end, if you go to high pressure, it's much more economic to use carbon molecular seed membranes. We also studied the fundamental of electrochemical compression and separation.
Here you see a few experimental points and the models. We, for the first time, we also tested the purity of the hydrogen after the separation and compression, which is very nice if you use methane, because then methane really doesn't pass through the membrane, and you have more or less 100% of purity at the outlet of the electrochemical compressor. But we also identified some problem with CO and CO2. And we published quite a number of papers on this, and here are some models that we use for the scale up of the system. Again, we took into account all the phenomena occurring, and we have a complete model. Of course, it's a new system, so we have to compare to standard system. The standard is PSA. Here you see a comparison between the hybrid system, the small one, 25 kilogram per day, and the PSA for the same separation. Of course, PSA is not working very well when you have very low concentration of hydrogen. So you see here that the preliminary results show that the hybrid system is much better than PSA. Of course, you know that you can improve the PSA if you put a separation before it, and it's also part of the study that we are doing. And here some breakdown of the impacts of the different parts of the hybrid project. Of course, this is quite advanced already, but still we have 8 months to refine this LCA results. And as I told you, we show one configuration, but there are so many that you can do with the 3 components. And here you see a techno-economic analysis with the purity reached with the different configuration, the cost, and the heat used for this configuration. Of course, this is related to 25 kilogram per day. If you go to larger scale, then the cost, of course, decreases. And some of the risk, unfortunately, we work only between TRL 5 and TRL 7, and I think most of the risk is not the component that we develop itself, but the components that should be standard components. What we found out is that most of these are too big for a lab scale and too small for a big scale. So delivery time of something that should be standard takes so much time and is contributing to the delay. About exploitation, what we did at the beginning is using the service of the European Commission. Here is a list of what we identified as possible exploitable results: membranes, compressor, TSA, system, and models. And what is nice is that during the project, we had 2 patent applications on the membrane and on the system. And we also created a company to exploit this IP. And the company was created at the beginning of 2020, and now has already 6 people working. So in a nutshell, 2 patent application, scientific publication presentation workshops together with other European projects. Also a PhD student was working on the project. She finished in May, and she's already working on hydrogen, which is very nice as well for the outcome of the project. And that is my presentation for today.
Perfect. Fausto, thank you very much for this. Very nice presentation showing us how combining technologies you can get a better achievement from the individual pieces, which is something hydrogen is all about. Actually, we have a very holistic approach also in the specifics of hydrogen purification. So thank you very much. We will see what questions this arises, because I think it was very interesting. I guess that people will have some questions to further clarify a few things. Meanwhile, we're going to move along into a very interesting part of the distribution, if you want, which is something to do with safety in pressed high or pressed Lee, or however, I'm not sure how, Thomas, you will pronounce it for me better. Thomas Jordan from the Karlsruhe Institute of Technology is the coordinator in a project that is dealing with safety aspects of liquid hydrogen. And please, Thomas, the floor is all yours.
Thank you very much, Enrique, for this nice introduction. We call it Presley. This is, of course, to have a reminder of our great singer. But first of all, it's dealing with liquid hydrogen. So we increase a little bit the density this afternoon. And I just wanted to show you some first results of this project. But before going into details, a little overview. So the project is based on the call issued in the year 2017. It was originally designed for 3 years. Now it's extended by 5 months, and the total budget was 1.9 million euros. So we are currently have completed 75 to 80% of our work. These are the partners spread over Europe, and so we have a strong consortium on research. However, this is not, sorry, I was clicking once too much. Let me get back. So before explaining a little bit more, I wanted also to motivate why liquid hydrogen safety is an important issue. We are seeing now many new applications, and even the existing ones are scaled up, and there is an increasing hydrogen demand. Therefore, liquid hydrogen offers now larger or even largest densities and some gains in efficiencies, and potentially reduces even the risks associated with hydrogen if you compare it to a compressed gaseous transport and storage scheme. So there are many knowledge gaps on the other side with respect to the accidental behavior of liquid hydrogen. And in particular, there are inconsistent and potentially over-conservative regulation codes and standards. So if you would compare the current NFPA 2 or IGA codes, then you would see strange inconsistencies. And this is based, of course, on a lack of knowledge. So the main objectives, therefore, were to close those critical knowledge gaps with an experimental program based on the outcome of this, I'd say, tuned experimental outcome on release, ignition, and combustion of those accidental scenarios and phenomena. We had to develop suitable models and engineering correlations which are suitable to be integrated in open risk assessment toolkits. This would provide enhanced recommendations for the safe design and operations of liquid or cryogenic hydrogen technologies. This, of course, then supports the international coordinated or harmonized development of standards by the standards developing organizations. So all in all, this finally would lead to an enhanced state of the art. And to do such a, let's say, major internationally harmonized activity, you have to have a strong network. And on this slide, you're going to see what kind of integrated approach Presley is. And it starts from the European institutions and partners, like the European Hydrogen Safety Panel or the Joint Research Center. And it reached out to those international standardization organizations like the ISO, IEC, or CEN-CENELEC. Beyond those bodies, we have partnerships with other projects which are also dealing with liquid hydrogen safety. In particular, it's a strong activity in Norway around the SHIFT project, but also H2 at scale in US, or those activities related to importing liquid hydrogen to Japan. Those projects have also strong contributions to the general issues of liquid hydrogen safety. Now you see here already some steps which were undertaken by the consortium. I'll get back to this later. This slide now summarizes the state of the project, or what has been achieved so far. And so we have defined the initial state of the art and the regulation codes and standards at the beginning of the project, and derived on this status the priorities. We executed the experimental program on the highly ranked priorities. We closed knowledge gaps with respect to release, mixing, ignition, and combustion. The ISO and CEN standardization organizations have been informed by the project. And already more than a year ago, we initiated the so-called preliminary working item 24077 on the safe use of liquid hydrogen in non-industrial settings. So the guidelines, which are now more or less extracted from the experimental findings and the modeling work, is now going to be injected into the standardization process, which has been initiated by this preliminary working item. Now, I want to give you a little bit more details. First of all, release knowledge gaps. It was absolutely unclear how a release from a container to a release point would behave, and how the phase changes within this tube system would look like. For this, we have developed a 1D model for multi-phase non-equilibrium discharges. Secondly, we have defined discharge coefficients for nozzles in the typical size of 0.5 to 4 millimeters, which correspond to accidental breaches or fractures. And for pressures from 5 to 200 bar, meaning in the cryo-compressed domain. So the temperature range is from 20 to 300 K. So it means we also had warm reference tests. So we observed no rainout for horizontal releases, independent on the release height. Even for the large releases we did at the HSE sites. And there was a perfect correlation of temperature and concentration, which could be used for other purposes. Knowledge gaps on transient combustion. So if you release hydrogen, this is not an infinite steady state process, but there is a certain inventory which is released, and we did small inventory releases or discharges, and we tried to identify worst case ignition locations and ignition timings for inventories of filling an empty volume of 2.7 liters. And this again for a temperature range of 80 to 300 K for 5 to 200 bars, and similar nozzle diameters. Well, there is now a map available for the worst case effects which you might achieve with the different cryogenic inventories. However, we are limited to several hundred grams, and of course this has to be extrapolated to larger inventories if you want to go into standardization. Knowledge gaps which have been closed with respect to multi-phase accumulations with explosion potential. So there had been mainly two open questions which have been more or less answered to a satisfying degree. If you spill or spread liquid hydrogen different substrates like gravel or concrete or soil, you might observe benign behavior or extreme behavior, like on this slide on the right figure. You see a little pool which was formed repetitively with liquid hydrogen. And in this gravel bed, there was solid oxygen forming, which led to a spontaneous ignition, or let's say an escalation after ignition above the pool. And this was surprising to see such a strong event above gravel. So this, of course, will be translated into some recommendations. On the positive side, we found that if you would apply a water spray on a liquid hydrogen pool, you don't have to expect any rapid phase transitions, at least on those dimensions we did it, and under the weather conditions we had at HSE on those days. We didn't observe any dramatic event or any phase change which would be an issue. Now, the last slide on details I wanted to show you is on congested domains. And this is a major issue if you want to handle hydrogen, not only in the free, but also in buildings. And even if you would have liquid hydrogen there, you have to know how a combustion event would behave in a congested, confined area or domain. So we observed stronger pressure loads for cold inventories in comparison with warm inventories. However, as we use the same facilities for warm and cold tests, this implies that for the cold tests, we had roughly 4 times more inventory in same concentration mixtures. So additionally, we observed a change in critical and effective expansion ratios, which is important for flame acceleration considerations in cryogenic mixers. So it means that on one side, the mixtures behave more prone towards flame acceleration. On the other side, you need to have stronger mixtures to make them really critical mixtures. What we observed additionally is now another transient in combustion, which is the so-called deflagration detonation transition. And there we saw a tremendous reduction in the so-called run-up distance, which means that those mixtures behave a little bit more likely to run in a detonation in those obstructed and confined areas. However, what was a little bit surprising is that the usual strong impact of congestion is not as strong on those highly dense mixtures at cryogenic temperatures. Still open is the effect, these effects in the free for large inventories. So to summarize and to show up with to explain how we wanted to exploit these results, after closing these knowledge gaps and enhancing the state of the art, we are partially on the way to include those models in risk assessment methodology. We derive recommendations for users directly or for standard developing organizations, and we are initiating a review or a development of a new standard with these results. The impact will be that we enable the safe and economic introduction of liquid hydrogen or cryogenic hydrogen and associated technologies with a flexible but robust framework consisting of improved knowledge bases and consistent recommendations and performance-based harmonized specific standards to be referred by corresponding regulations. Now, my last slide is an invitation. The dissemination conference of PESLI will be in the next year, really close to the end of the project in May. We still hope to be able to have a physical presence in Athens at the partner there. However, it's very likely that we turn this into an online video conference. So thank you very much for your attention. And of course, also the thanks go to the joint undertaking for the support.
Thank you very much, Thomas. Very nice presentation. Very interesting subject, I have to say. We have to be prepared because liquid hydrogen is something that will probably come at some point in some stages of the distribution line. So very, very, very necessary to be ready. And I'm sure that you will have plenty of questions about this very interesting subject. I also have a couple already prepared for myself because I think it's fascinating. And now now we move into another possibility for the transport of hydrogen. This time coming from Hydrogenius, a very nice and strong SME that is arriving now to the market very, very strong. And as from the European Commission, we're always happy to see these initiatives coming forward, because we have to go from the university towards also enterprises. The project is called HyStock, and Ralph Otto is going to introduce us about liquid organic carriers, liquid organic hydrogen carriers, of course. Ralph, please.
Thank you very much, Enrique. And I hope you can see the screen, and I see my writings, my letters are mirrored, but nevertheless, thank you very much, Enrique. Good afternoon to everybody. And today my presentation is about LOHC. What is LOHC? It's actually just about this little bottle here, and you've heard something about safe and efficient storage of hydrogen. Now here, this is really safe. I have it in my room at home to little children. Hydrogen is stored in a liquid. That's LOHC. And I will come to that later. First of all, I will introduce you to the HyStock project, which we are working on. So, first of all, the HyStock project also comes from the call in the year 2017. We started it in 2018, and now it should be ending right next month. But we asked for a project extension because we know the LOHC technology. We know how efficient and efficient and safe it is. But of course, now we want to bring it to the world. We want to do real projects, and that's what we did actually in HyStock, and there are a lot of challenges. I will come to that later on. So that's why we extended the project duration a little bit, like the other projects did as well. And currently we're at a status of about 70%, and we had a total project budget of about 2.5 million euros. Now, who are the partners? They are all over Europe, but with a sort of location in the north of Europe, Finland, and of course Hydrogenius from Germany, as well as Hygear in the Netherlands, and in Finland it's Wojkowski and VTT Technical Research Center. So, what is the project about? We want to produce hydrogen in Kokkola in Finland, and then transport it via the LOHC technology to VTT and dehydrogenate the hydrogen, or the LOHC, the loaded LOHC there, in order to get a certain quality measurement. How good is our substance? How good are we with the unloading process? I will come to that later. And after this testing at VTT, actually, the release box, so you will see some pictures of it, will transport it to Wojkowski in order to supply a real refueling station. So we are, regarding technical readiness level, right above on the real automotive process, and you're really using this hydrogen and transport it on a cost-efficient way. It shall be fully automated LOHC hydrogen storage and release system. In the end, that's our objective. We want to demonstrate the suitability of LOHC for the commercial rollout. And of course, we want to reduce the capital expenditures, the investment, and the operative expenditures during operations for storage and transport of hydrogen. So, once again, coming back to this little liquid, the bottle, usually I have 1 kilogram of hydrogen at my home, and in a 16 kilograms of LOHC liquid. Now I have a small bottle only due to the corona crisis. And what is it all about? So right above you see a little box which is called hydrogenation. So we want to get the hydrogen, and in this little box we hydrogenate the liquid organic hydrogen carrier. So something like this yellow liquid, put hydrogen in it. When we do this is an exothermic process, so we get heat out, which we can use, for example, for local heating or if we go not to Finland, but to the sub-Saharan Africa or Middle East, we can also use the seed for desalination, for example. Then we can transport the hydrogen very easily, very safely, cost efficient with the existing infrastructure towards the site where we have to dehydrogenate it. So the next box, there we dehydrogenate the LOHC, get hydrogen out, and use the liquid again to hydrogenate it above and all along something like a circular economy, like you know from the bottles, which you use more often than just one. When we have to dehydrogenate it, we need some heat in. All in all, the efficiency of the process is about 90%. That's our target. Right now, of course, this is in research, and we still do have to do a little bit of work there in order to get the efficiency of about 90%. But what are the advantages of this liquid organic hydrogen carrier? Besides the efficiency, it's of course it's non-explosive. It's a diesel-like liquid. It's hardly flammable. You have it liquid until minus 39 degrees of Celsius, and you can store it at ambient conditions. And LOHC, the one we are using, is a commercial heat transfer oil, which is, for example, produced in Germany. So if we go to the next step, looking at the storage system, so we have always two systems, the storage system above, which you have already seen, and the dehydrogenation system or the release system. So for the storage system, this was already successfully commissioned and tested in Erlangen, approved by the TÜV Süd, and has been shipped to Wolkowski. And actually yesterday we have not just the assembly was already has been completed, and the storage box is finalized in Kokkola, and yesterday we had the first fully automated process. So we are quite thankful that although we have the Corona crisis, which is quite kind of hard if you have a real project, a real site where you want to show something in reality and have a commercialized system in the future. But we are really thankful that this works. And the storage box now can produce hydrated material and transport it to the release box. And if we look at the release system, so we have already preparations at the test site in VTT. We have assembled the system. There you can see a picture where we really did something. So here you see where we worked on this project, on the release box. And it was shipped actually on the Friday, the 20th of November. You see some pictures later. And now the on-site commissioning in Finland starts. And in January, we also want to start the quality measurement. So what is the general status? We have about 70% already achieved. We are really looking forward to also get the rest of the project finished. It was quite a challenge, but we are really happy that we had such good partners where we could actually work together and find solutions for all the challenges which arrive if you are not in just research, but in real life projects. And here you can see the truck with the release box leaving our headquarters in Erlangen, Germany on Friday. And now it already is there in Finland. It arrived safely there. So what are the risks, challenges, and lessons learned? Well, first of all, I already told you. We have COVID-19. We have the Corona crisis. This is really challenging if you have a real life project and you want to deliver something. You have to standardize and you have to discuss it with your suppliers, and you have to get something in to real life to work automatically. This is slowing down the project processes. And we are not a standardized system. We are not like a car manufacturer, but we have a new project. We have a new technology which we have to prove. And additionally, I mean, we have technical inconsistencies due to different specifications of the several suppliers we have in the project. It's just natural. And again, as soon as Corona or COVID-19 arrived, this was even more challenging because we have to standardize, and we are starting to do this with this project, and it helps us a lot. And last but not least, the exploitation plan, expected impact. Now, the results are described in detail in the individual deliverables, which will be uploaded in the EU portal. It is quite kind of very positive for us, and we have many lessons learned. We have to standardize, we have to bring a commercial viable project to real life now, and we are actually very, very thankful for all the support from our suppliers, from our partners, but also the European Union. And the next steps, perhaps we are very involved also in the important project of common European interest, because LOHC is the only viable technology right now for importing or transporting hydrogen in a very short moment of time from one place in Europe to the other place, from Romania to Spain, from Spain to Germany and the Netherlands. And there we are quite involved and thankful that the European Union helped us to develop such a technology and helps us to get to the next steps of this commercial viable technology. And that is the end of my presentation, and I am thankful to get all your questions regarding our technology. Thank you very much.
Thank you very much, Ralph. I'm happy to see that you are so confident with your technology, which is very good. We need this technology. I'm not 100% sure whether it's the only one, as you state, but I do agree fully with you that it will play a big role in this world where we are going to have to move a lot of hydrogen. So right now we have come to the end of the presentations. I'm going to put you some questions already coming from the audience, and I will have some prepared also for myself. We have seen all the stages or different stages of the transport and or moving hydrogen, logistic of hydrogen, also storage. The first question I will try to go in order of the presentation. So I will start with Hiker, Marcelo. Please, I have something like 5 questions for you. Some very specific, so I hope that you have the answer ready, because I'm not sure in my project I would be able to answer, but okay, let's give it a try. What is the thermal range of the temperature range of the thermal energy buffer?
Well, actually, the temperature range is one of the big issues of the project. In principle, if you have a system that is simply changing the pressure, you could stay in the single temperature. But of course, we have to manage this absorption and desorption together with the phase change materials. So at the end of the day, we have a temperature about 55 degrees C, and the goal is to play plus minus 10. This is the goal. But because the metal hydride needs to be activated at least the first time, we are planning to have activation at a bit higher temperature. But during running, the idea is 55 degree plus minus 10, roughly speaking.
Perfect. Very manageable temperature, I guess.
Yeah.
And then, of course, the next question is obliged, is how does this technology compare to compressed hydrogen, which would be the easy alternative?
Yes, actually, this is one of the issues that we are managing in this techno-economical analysis, and the goal is to compare the solution that we have at the moment. At the end of the day, the goal is to put 50 kilos of hydrogen inside of the standard container. Everything is included inside of that. So, of course, if you manage, hydrogen as a compressed gas, you probably, in order to have in safety condition inside of this container, to use quite higher pressure than what we have right now. So at the end of the day, you have to add compression costs and so on. So in some sense, this is a comparison that is running in the project. And I thank you very much for the question, because of course, this is crucial.
Okay, nice answer. I understand. One question, and I'm not going to follow the order that I've got, but do these materials suffer any type of degradation, and how do you deal with it?
Well, actually, in this specific field of research, degradation is something that you could manage in 2 ways. One is simply cycling up and down several times, and then you see if the gravimetric capacity is losing something. And we already performed a lot of cycles up to about 100 or something like that, and we didn't check any change in the absorption quantity. And the second crucial point is the poisoning of hydrogen, because if you get hydrogen coming from an electrolyzer, you could have some poisoning. So we are running experiment in clean and dirty hydrogen in order to check if there is any poisoning that can change the life of the hydride itself. And at the moment, the results are very, very positive. So in this sense, it seems that the alloy that is based on iron titanium is not very much suffering about this, let's say, slightly water contamination. I don't know if you answered the question.
Perfect. Thank you very much. Yes. And one last question from my side. Regarding the state of the art, how does your technology compare to the competitors in other metal hydrides, and also how does European technology compare to the outside world? Are we competitive in this field?
Well, this is, thank you, Enrique, for the question. In some sense, when you compare different materials for hydrogen carriers, in the solid states, you have to very much take into account this temperature range. So the goal of the project is to be able to play below 100 degrees C. So in this sense, we have to manage mainly with the metal hydrides. So at the end of the day, this iron titanium that in our in our running condition is storing about 1% is very much comparable to other metallic systems. If you go to magnesium, for instance, that is storing a bit higher amount in terms of gravimetric density, of course you need to go to much higher temperatures, and that is changing the story very much. And the other point is, because this is mainly thought for a stationary application, at the end of the day, gravimetric density is not the key point, but it's moreover the volumetric density. And this, for this specific material, is, let's say, in the top range of intermetallic compounds. So in this sense, we selected the material mainly for the volume gravimetric density rather than to the gravimetric density. And comparing the Americans, the Japanese, or the other people around the world, well, of course, we are in contact with the other people playing in these fields. I would say we are quite aligned. That is for sure that this system that is playing in this project is storing 50 kilos with metal hydride, and there are very, very few examples in the world that are running in this way. So this is aligning Europe together with the Japanese that are running mostly in this direction.
Perfect. Thank you very much for this very nice explanation, Marcelo. It's nice to see that Europe is still in the race. I mean, we're with the technology, and now I'm eager to see this being commercialized and making sure that you do the next step and reach to the commercial prototypes and put it in the market. We're going to change now to questions dealing more with hybrid to let you rest. And if I get more questions from you, for you, Marcelo, I'll continue. But now we're going to go to Fausto. I have some questions regarding the membrane versus the rest of the system. What is the most expensive part of the system?
If you take the system with membrane TSA and electrochemical compressor, at the moment the electrochemical part is the more expensive. It's also because it's a new system and has to be scaled at the scale that we want. But at the moment, is the biggest cost is there.
Perfect. It's good to know that although it sounded palladium, it's the electrochemical that is more expensive. I would never have said, but okay, fair enough. Another question that is interesting coming from the audience is, of course, we are worried about where to use the hydrogen, and of course, we're talking about purification. Can you use this the hydrogen coming out of your system directly for cars, for automotive standard?
For the purity, yes. For the pressure, not yet, because what we looked at is having a separation that can be used directly in the fuel cell and not in a storage system. So basically, when we have the hydrogen is just above 1 bar, so you can fit to a fuel cell. If you want to store in a car, of course, you have to again pressurize and put up the pressure that can be stored. But the purity, yes, you can use directly in the fuel cell.
Perfect. Yeah, I fully understand that coming from a TSA, it would not be at too high pressure, so I guess you would always have to compress it. Another question would be, of course, everything is about costs. Sometimes we are dealing with hydrogen that is costly because compared to some other fuels or energy carriers is costly. How much would this piece of the value chain will add to the cost? How much does it cost to and let's talk about for a car is 5 kilos, or if you want to go for 1 kilowatt hour, for a more technical audience, would be also the same.
Yeah, no, actually we had a cost that was a cost target that was 1.5 euro per kilo on the scale of 25 cubic meter per hour. 25 kilos per day. I'm always used to cubic meter per hour. Sorry. And we are just below that. So it is below 1.4 euro per kilo. So it's not cheap, of course. You have to separate from a very very diluted stream. If you do with PSA, you can reach also 8 euro per kilo. So that's why we are much better.
Good to know. And then I'm going to ask the same question I asked Marcelo. How is our technology in Europe compared to the rest of the world? How are we doing? Are we in a competitive scenario?
I think so. I mean, what we do is a combination of technologies. We have IET is very well known for electrochemical compressor. I think in US there is also study and companies doing that, but IET is doing quite well. For the membranes in Europe, we are in a very good position. As I said, we just created a company to commercialize the membranes. They are now building a production line for membranes, so it will not be done a lab scale 10 membranes per time, but we will do 300 to 400 membranes per time. So we should be ready to sell to companies. Of course, there are also other companies. There is Sintef working on membranes. There are other companies working on membranes in Europe. So I think we are in a very good position.
Okay, thank you. And one further question. We are talking about low concentration streams. How low and how high? Or is it a question of combining the three technologies so that you can cover many ranges? What would be the highest and what would be the lowest?
You can cover many ranges. Why we selected 10%? Because when we wrote the proposal, there were some studies on the concentration of hydrogen in natural gas grid, and the studies show that below 10% there was no risk. So we selected 10%. If you go to much higher concentration, then the gap between our system and other system will decrease. So I would say that we are very much cheaper, up to 30-35%. And then the more hydrogen there is in the system, the lower is the gap with PSA. If you go to extremely high concentration, then of course the gap with PSA will be very low.
Okay, very nice. While I get more questions on this subject, I'm going to pass to Thomas. Thomas Jordan, you are touching a very interesting subject, and I think people are very eager to learn about it. One thing that everybody has in their mind right now when we talk about liquid hydrogen, especially because if you follow the press or the announcements lately in Twitter or in LinkedIn, etc., you see that Airbus has announced that by 2035, if I'm correct, they're going to move towards the use of hydrogen for their aircrafts. You dealing with liquid hydrogen, how do you see this movement? Are we very far? Do we have to do a lot to reach the safety requirements to go for the aeronautics? Or
well, first of all, the application is not far from the traditional application of liquid hydrogen in space. So, secondly, you have to consider that regulations are really different from standard regulations if you look into aviation. There are pros for liquid hydrogen, which have been, of course, published in the recent study of the joint undertaking and Clean Skies, where the advantage of having liquid hydrogen for, let's say, short to mid ranges is obvious. from the economic point of view, and the risk perspective is such that, well, first of all, liquid hydrogen has, in general, a slightly lower risk potential compared to compressed hydrogen. Therefore, I would fly easier with liquid hydrogen than with compressed hydrogen, to be honest. There are some issues regarding treating liquid hydrogen tanks or having huge inventories in closed rooms like a aircraft vessel or such a hull. And this has to be solved. And another point which has to be solved there is free-form tank systems. There were some precursor EU projects like High Store was the name. No, Store High, sorry. And they were looking already for automotive applications into free-form tanks built with plastic materials. And I think there's a huge potential in introducing lighter and cheaper materials for cryogenics. So yes, there's a huge potential, I guess. The main point is, of course, supply of liquid hydrogen, which, well, has to be solved in parallel.
Of course, we have to solve a lot of hydrogen production issues because we really need a lot more hydrogen than what we have right now, and hopefully everything will be green. One question about liquid hydrogen is not on safety really, but maybe you know about it, and I know that the audience would be eager. How much energy do you lose in the liquefaction, and can you use it that coldness after when you deliver the hydrogen? Can that heat or lack of heat can be used?
Yes. Well, based on the lower heating value, you usually invest currently up to 30% of the energy of hydrogen to liquefy hydrogen. But these processes are not designed for commercial supply of liquid hydrogen. They are designed for supplying actually specific industries like space, where typically costs are not the same pressure like others. So, but this is changing. So, and there are interesting studies which claim that by changing the way how you use different kind of coolers, you can reduce the amount of energy required for liquefaction still by, let's say, factor 2, so that you end up with something in the order of 15% of the lower value of heat of hydrogen, meaning 120 megajoules per kilogram. So take this or 15% of this, and this would be an optimum liquefaction plant. Of course, size still matter there, and this is still big block technology at the moment because you have huge temperature differences, and the cold boxes have to be huge to be efficient. So there's potential, yes. And compared to compression to 1,000 bar or 700 bar, there is almost no difference, to be honest. And maybe I should mention this: there is also a potential use of cold temperature. Although it's not the best cold supply, but it comes with some chemical energy. But there are some interesting, let's say, uses, especially in combination with superconductors. So high-temperature superconductors perform perfectly with liquid hydrogen compared to liquid helium, which is much more expensive than liquid hydrogen. And this combination, in the sense of sector coupling, meaning superconducting electricity combined with chemical energy storage, seems to be really, really exciting. So we are currently pushing this technology here at KIT a little bit, but we hope to find, let's say, support by the industries there.
Perfect. Thank you very much, Thomas, for these very nice explanations. We're going to move now to the hydrogenous. I think you've managed to turn around the letters so that everybody would be able to read them, because it was a bit confusing at some point. Ralph, thanks for that. We have a couple of questions for you now. Basically, they are dealing with capacity. So you talked about that this is a very easy way to move hydrogen, or very optimal way to move hydrogen. But for a truck, we see it compressed hydrogen maybe moved in trucks. How would your technology compare? How much hydrogen can you fit into one of these 40 tonners?
Yes, thank you very much for the question. Yeah, first of all, we can about in 140 food truck, we are preparing right now in another project to transport about 1,680 kilograms of hydrogen. So if you take the current tank trucks, it's just the same technology more or less, which you use for oil right now, and we are doing some minor changes, and then it's about 1,680 kilograms, or in other words, in 1,000 kilograms of LOHC, you can transport about 60 kilograms of hydrogen.
Okay, and just as a comparison, how would that compare with liquid hydrogen? I know that it's not 100% fair comparison, but okay.
No, but it's a good comparison, because with the liquefied hydrogen, I think it has advantages, and as you mentioned, of course, the LOHC technology is not and will not hopefully be the only technology to transport hydrogen. We need a mixture of all different applications, and especially liquefied hydrogen has its applications already in the space industry and will get in the aviation industry. But about if you look at a 40 feet truck for liquefied hydrogen, I think it's twice as much. But of course, completely different technology. So I think what I've heard is 3.2 tons of hydrogen, whereas we are about 1,600 or 1.6 tons. And to gaseous hydrogen, depending, of course, on the pressure, it's about 400 to 800 or 300 to 800 kilograms of hydrogen in such a truck. But always very different types of technologies and very different uses of applications, of course.
That's a very interesting answer, actually, and I would like to build on that. And in fact, I would ask this later on to the rest. Which type of application do you see your technology focusing on? Because we know that right now we have to solve the maritime sector, we have to solve the aeronautic sector, of course, the heavy-duty truck sector, and the different stationary scenarios. But which one would you think your technology best fits?
So we are looking at three different applications. First of all, the large-scale import of hydrogen to Europe from, for example, Africa or northern part of Africa, Chile or Australia, where of course we have also liquefied hydrogen as competition, or green ammonia, of course. But we think due to the usage of existing infrastructure, it can be way cheaper to use our LOHC technology, because we don't have to change the whole economy and the whole business. That's one of the first application. Second application, which is also very good advantage of our technology, is we can bring it directly to the customer, to the industry, for example, and as soon as there is excess heat right at the industrial application or customer off-taker, we have a sweet spot for our technology, because we can deliver the hydrogen, store it safely at the customer, and then dehydrogenate it with the energy or the heat he has got in excess, for example. And third application is, of course, the mobility sector. So we can bring the hydrogen to every end customer very safely, meaning also to refueling stations, especially those refueling stations for bigger logistics, so heavy duty trucks. And additionally, mobility also means that we could use it for ships. We are doing quite a bigger project with some Norwegian companies right now to directly using LOHC in a ship where we can use the existing ship infrastructure or tank infrastructure and have the excess heat used to dehydrogenate the loaded LOHC and then use a fuel cell, for example. So we don't have safety issues too much on a ship, and that's also an application for us. The same goes for trains, actually.
Okay, very nice. And just before I ask the same question to some of the other panelists, how much cost do you add to the logistic of hydrogen?
Well, in the end, that's the most important question, because it will only be the cost whether you transport it via gaseous form, liquid form, ammonia or LHC or methanol, or you compare it to on-site electrolysis. So it's in the end, it's the cost and the advantageous handling and safety of how you transport it. And we did a bigger study right now, finished this also with Roland Berger, which we will publish in the coming weeks or months, that we are about the same cost efficiency as ammonia, way cheaper than liquefied hydrogen, because we don't have to invest in the infrastructure too much in comparison to liquefied hydrogen. And so it will be about the same cost or a little bit lower than green ammonia. But still, of course, we have to do a lot of research and more project upscaling for this. But just to give you a sort of comparison where we are right now with our technology, and which is quite competitive compared to the other technologies and has some advantages, but still every technology will have its place. I'm sure of that.
Perfect. Thank you very much. I'm going to ask now Marcelo a very similar question. Where do you see your technology? Where is the sweet spot for your technology, and how do you see your technology being in 5 years' time? Where will you be in the development of the technology? Will it be commercial or not?
Well, actually, the application that we are thinking about is mostly related to the stationary applications. At the moment, we are managing the system with about 50 kilos of hydrogen, and we know that this amount is basically for filling hydrogen for, let's say, 15 cars, not so much. But with such an amount of hydrogen, actually, you could support a house, let's say, in a standard condition, even for several weeks. So at the end of the day, as a sort of storage system for renewable in a small area, where the footprint is one of the key issues, we strongly believe this might be the location of the specific project. I mean, the results of the specific. At the end of the day, in the consortium, there is a very NG that is hosting the prototype that will be implemented next year in Paris. And they are very much linked to this, let's say, customer needed for storing of renewables in, let's say, some small areas, maybe something linked even to energy communities or something like that. So this, in some sense, is one of the main target. How will be in the future, that strongly depends on the cost of the material. And we strongly believe that in implementing the amount of the material, probably the processing cost of the alloy would be strongly reduced, and this might bring the system in a sort of competitive in some way. Because at the moment, one of the big issues is the cost of the material itself. But because it's a very niche application at the moment.
Okay, good. Let's hope that you manage to get there and with the cost downs and you do arrive to the market with your product. Fausto, I'm going to ask you a very similar question. Your technology deals with recovering hydrogen from the grid, for the natural gas grid. Of course, we all know that the technology right now, or the legislation right now, or the directives allow for a certain percentage, but it's true that in the future they might increase this amount of hydrogen. So I guess you have a window frame for your technology which is not that long. When do you see yourself being ready to use this technology, and for how long do you think this technology will be applicable? Fausto, please.
Yes, thank you for the question. We have different market in principle. For the small scale, the company has in the business plan to commercialize the technology in 3 years from now. So
3 years. That's really nice. Very.
Of course, it depends on how many customers there will be and how fast the legislation will allow to have enough hydrogen. At the moment, for example, in the Netherlands, is very low, but we know that there are a lot of discussions on increasing this concentration.
Okay, and one question that was coming from the audience, but I forgot to ask before: the natural gas. Of course, you are extracting the hydrogen from the natural gas, and then do you have to put the natural gas back into the grid? And then, if you are doing that, I would guess that you have to give it back at the same pressure level. So, how does this affect the full system?
Absolutely, that's true. I saw the question as well. Yeah, that is why the compressor or the separator has to have very low pressure drop, because we re-inject the natural gas in the grid. So we have around 200 millibar of pressure drop in total. So we have to give back at the same pressure. The system is tested at 8 bar and 40 bar at the moment.
Okay, so and yes, I understand. And now my curiosity then, you're modifying the concentration of the hydrogen in the natural gas, so you're changing the composition of the natural gas. How do you see this being managed? Because then I'm going to get a different natural gas than the one that was coming originally. How do you see this?
I think this is a point that we didn't touch in the project, but I think most of the comments and the contacts we got till now are from people that manage the grid. So I think they will be the first customers, and probably they will have a range in which the hydrogen concentration is delivered. And by the way, there was also another question. We don't remove 100% of the hydrogen. It would be very, very costly. We reach 95% maximum.
Yeah, I was assuming that you would be leaving some hydrogen there. But it's nice that you answer also that because I will just explain. There was a question from the audience asking whether you take absolutely all the hydrogen out of the pipeline. I understand that it would also be very, very costly, basically, just to retain. But if you look at PSA, that's something that they also do. They consume part of the hydrogen to purify it, so it was a normal thing. Okay, thank you, Fausto. Now I'm going to ask Thomas one question. Of course, you're dealing with PNR research. Your product, if I may call it like that, would be ISOs or norms. And when do you think we will have an ISO that is there ready so that we can use hydrogen for heavy-duty trucks? Because we are always talking about that for trucks, liquid hydrogen might be one of the options.
Yeah.
And we know that this takes some time. When do you think this could be ready?
Well, the schedules on ISO are more or less quite a rigid system, so you have to follow a certain procedure. By the way, there's currently a set of 2 standards possibly under review. You know that beginning of December there is the plenary meeting of the ISO TC 197. And there are 2 quite old standards which were formed during the BMW liquid hydrogen adventures. They have more or less given cause to develop those 2 interface standards, which are still there. And there had been requests to review those standards. So possibly, if everybody agrees, there will be a working group installed at ISO, and they will rework or work on those 2 standards. However, those 2 standards are designed for small inventories, not the 100 kilograms you typically use at the trucks. So for this, of course, you cannot do it in a let's say technology separated space. The outcome of Presley would be rather going into a more generic technical report, which is corresponding to the TR 15916, which would effectively maybe extend the existing TR 15916 for safety considerations with hydrogen. So it will be rather generic. The more specific one requires actually industry players to push their technology and to suggest them for standardization. So if so, an industry player would get at this level either Senelec or ISO IEC, then it would need still, I guess, roughly 1 year. This would be the typical time frame where a technology would be proven as a sort of standard. However, as this is quite early, I at least have the impression from the industry that they hesitate to push this at this early state. So I think this is still evolving and nobody wants to fix something specifically at the moment, rather wait for approval or validation of their specific technology and then possibly go into such a process.
Okay, I understand. I'm afraid that we've run out of time. Thank you very much to the people that have presented and given us their insights of their projects. Thank you very much to all the audience, and I hope to see you at least in the awards that are later on this afternoon. Thank you very much. Bye-bye.
Thank you.
Thank you.